All right. Welcome everybody to second office hours. This week we will be covering divide and conquer algorithms, approaches, sample solutions, and sort of how to approach these problems and understand what the reasoning behind doing divide and conquer approaches are. Again, just as normal, we will be recording these office hours. It will be posted after the office hours is over. So if you decide you want to talk or type into chat, that it will be recorded and it will be available for other students. Taking a look at the homework 2 practice problems. Cool. Let me download this. Divide and conquer content is actually pretty light, but going over the practice problem should fill out the rest of the office hours. Okay. Some questions already. If there's some questions about dynamic programming, I will not be covering any dynamic programming problems or questions today. There will be another office hours or maybe a couple after this that goes over exam prep, and I will revisit dynamic programming at that point and try to ask questions then. General question about dividing. Do we have to explicitly state the cases if a case is eventually evenly divisible by whatever factor we are using? In general, the divide and conquer, sometimes we will give you this, we will tell you that the initial input is a size divisible by 2 to make things easier. Other times we will not. In some cases, handling a odd number is important. In some cases, it is not. So it really depends on the problem. When in doubt, just put in, if the number's odd, do this. I will say for binary search, when we get to it, we allow you to do low, high, mid. We don't really care how you calculate mid, and so you don't need to state it. You don't need to do like floor of high minus low or ceiling of high minus low. We assume that the mid will be picked in a way that the algorithm works. So I suggest you don't actually tell us how to calculate mid unless it's important to the actual question. There are some situations where your mid is not quite the mid of a normal binary search question. And so you do have to tell us, oh, my mid is actually this, or my target is actually this, and this is how I would calculate it. But in general, if you're not doing anything special, you can just say, we take mid and we do this, and that's good enough. Okay. The cache question before we start.
So on the same point, right? For the binary search we don't have to explain that, but I know the base binary search basically has 3 things, right? The left array, the right array, and the mid array. If it matches with mid, pick mid, otherwise go left or right. But there are some problems where you only break it into 2, right? Even if the mid, you're not selecting actual point, but maybe the smallest element or something. And sometimes you go from, if you want to go left, you go from 0 to mid, including the mid. Do we need to provide those kind of explanations, or is it assumed that the algorithm will be designed in a way that we don't miss anything?
I think if the question requires you to have mid on one side, the other, or both, you need to specify that, because binary search will generally discard the mid on one of the sides, right? So if you, there are some problems that will be like, okay, I need to keep track of the mid because I need it in both ranges. In that case, that is a special modification that you need to call up.
Thanks.
Yep. All right, let's get started. So divide and conquer solutions in this class take on a different form as dynamic programming. So you need to be careful that you not to repeat the same template or the same parts. Okay. So we have the algorithm part. This is the part where you tell us how your algorithm works. There is no pseudocode involved. You need to include the base case it's needed. Your divide and conquer is a recursive algorithm, and so it goes back, or it gets smaller and smaller or it divides more and more until it gets to some base case and makes a decision, and then that solution bubbles up to the top. So unless you have a base case, there's no sense of how your algorithm is going to stop itself before it returns. Explain what part of the black box you want to modify if needed. So in this class, when we do divide and conquer, you do not have to write the full algorithm. As long as you are using a black box, you can go and say, oh, I'm going to use binary search. And the only difference between the normal binary search is I'm going to do this instead. Or I'm going to use merge sort. And instead of doing the merge, which is normally to compare two elements, I'm going to do this instead. So anytime you have a black box, you can just go modify specific parts of it. The black box you are allowed to use for this class is provided to you in a post. So go and read up on that and see all the different parts that make up that black box. And then so you can easily say, oh, I'm going to modify this direct thing. So that's important. And if you don't modify something in a black box, we assume it runs as is, given what we say the black box does. So you can't say, oh, I'm going to modify the merge part of it and then assume it's going to do something else down further down merge sort because you modified that part. You have to tell us exactly what you want your black box to do instead. Okay. And the more you write, the better, right? Like you don't want to write like 3 pages worth or like a bunch of words just to get them in there. But if you're not sure whether we are going to assume something based on your description, just give it a little bit more detail. Say there is a big penalty that says branching does not have enough. Like branching is the idea. Branching or steps is the idea of like which way you go in your binary search or what you do at each individual step that you're trying to modify. And there is a rather large penalty for not giving enough detail. If you say something and you just assume, oh, someone who's read this should know what it means, I would more err on the side of like, oh, this person probably doesn't know exactly what I mean, and I'm just going to, explicitly talk about it. But one thing that you have to be careful about is that the more you write, the more opportunity you give yourself to describe what you're trying to do, but also get a opportunity to contradict yourself. So even after you write a lot, make sure you go through and see that there's no contradiction between your statements. Because if you write 2 statements and they do 2 different things, you're going to lose points for that. The reader's not going to assume one is the one you meant and the other one is the one you don't mean. So you got to be careful. Okay, it's a balance. Learn through it using homeworks. Bullets are allowed but not preferred. I tend to write my solutions in bullet form, but that is actually I've been trying to get away from that. You wanted to give it a sort of a narrative form if possible. You're trying to explain to someone what your algorithm does in sort of a paragraph form, if that makes sense. See. Sub-bullets are further discouraged. So you don't want your solution to start looking like code. So you don't want a bunch of tabulated statements of like anything that's like like an if-else statement or like a while loop. Anything that looks like that is going to look like code to your grader. Rather, what you want to do is explain. We're going to if our target is less than mid, then we are going to branch a certain direction. If our target is greater than mid, then we are going to branch a certain direction, and do it in like a one single sentence form instead of like if this, then this, if that, then that, else, stuff like that starts to look like code. And there's a gray area of like what is code and what is clean writing, and you want to try to kind of stay away from that gray area if possible. Avoid variable assignments or function name calls. Use words instead. Let's consider the midpoint. Let's consider the target. Like those have meaningful names in sort of binary search and divide and conquer algorithms. So try to use those instead of saying let x equal to this or set this to equal to that. That tends to look like code to some graders. The second part is your justification of correctness. So after you write your algorithm, you have to explain to us why your algorithm works. It's not enough to just write the algorithm and walk away. And this is actually very similar to any sort of coding interviews that you might have at a tech company. Most tech companies aren't okay with you just writing code and be done with it. You have to practice being able to explain what your code does to someone even after all the instructions are given. Okay, so why did you pick a black box? Anytime you pick a black box to modify, there's a reason you are doing it, and you need to explain what that reason is. One particularly common one is binary search. I picked binary search because, and that because is almost always because your input is sorted, right? I picked merge sort because I picked more sort because my array isn't sorted, and in order to continue with what I'm trying to do with my algorithm, I need the array to be sorted. Therefore, I use merge sort. So explain why you use every single black box you use. Why did you make modifications to a black box? If you modify binary search to do something rather than what it normally does, there's a reason you did it. You didn't just do it because it felt fun to do. I modified the target on each recursion because I needed to have a dynamic target because of the following. I branched to the right instead of branching to the left normally because I needed to do this, and reasons why you made modifications. Why does your final step in your recursion solve the problem? My algorithm returns, this, and this is the solution to the problem because. And it could be as simply as because it's exactly what the question asked for, right? I returned the first 0 because that is the answer to the problem, and that's fine. That's it, right? But if you're, saying, oh, I returned this special target, it could be, because of certain conditions that it meets in order to be your solution. Okay. And then finally, runtime analysis, and this is different than implementation analysis of the divide and conquer. Whereas that was, talking about your subproblems, your number of subproblems, your runtime, your final index extraction. All we care about here is the overall runtime of your entire solution. We do care about how you arrive at that runtime, which is a little bit different, right? Like in the divide and conquer, you just give us a final runtime and we go, oh, yep, that's the correct runtime, and you're done. Here, you need to tell us why your runtime is what it is. And there are certain aspects to it depending on how the problem is being solved. If you are writing a brand new solution that doesn't use the black box, which by the way, you're allowed to, you can write a complete solution from scratch in divide and conquer and not use any black boxes if you think that's the best approach to take. In that case, you have to break down your solution into the parts that tell us what that runtime is. If you decide instead to modify a black box, which again is a perfectly valid approach, what you can do is you can tell us what the runtime of that black box is initially. So like binary search is log n. Okay, that is a known runtime. You don't have to tell us how that log n comes from. You just say binary search is log n. My modification, you always have to tell us about your modification. My modification does not add any additional work to each step, and therefore the runtime remains log n. You have to tell us any modifications you make and how that affects runtime. It could have no effect. It could have some effect. It depends. So you just have to make it clear. Okay. You can also calculate the recurrence using the master theorem. Okay. So there's lectures about the master theorem. It's also in the book. Make sure you understand it, and then you can just tell us how the parts of the master theorem is counted, and then you just solve for the master theorem. You don't have to go through the math and tell us how the master theorem is solved. You just have to tell us why A, B, and D are set the way they are, and that's one easy way to sort of give us to your runtime. Yeah, again, you can assert the runtime of known algorithms, call it modifications, even if it's all one, and yep. So any questions about the solution of a divide and conquer problem? Bradley?
For you said you have to justify A, B, and D for the master theorem. Is that just like this? When I approach it this way, I break it into two subproblems of size n over 2, and for each of those, I do O of 1 work or something like that.
Exactly. So you just say, oh, I am dividing my problem into 2, 3, 4 subproblems, and that's my, that's B. Of those subproblems, of those breakdowns, I do work on 2, 3, 1 of them. That's my A. And at each recurrence, I do O n work, O 1 work, O n squared work, how much work that is, and that completes your master theorem, and then you just solve it, and that's it.
Awesome. Thanks.
Yep. Aaron?
Hey, Joves, can you hear me?
Yes.
Thank you. Sorry, I had to give permissions. So when in the runtime analysis section, if we run into a case where we need to use substitution, how detailed do we need to be? Like, do we need to go through the entire, I guess, like every step of the substitution, or like can we truncate it? I guess what level of detail are we expecting there in that case?
As much as you want, as little as none, right? So once you have come up with the master theorem, like once we confirmed all the different parts on why you created the equation of your master theorem, how you solve that master theorem is up to you. You can use substitution, you can use comparison methods, you can use just throughout the math that is given to you. Like, we just care about the setup and the final answer, and everything in between is sort of up to you.
Got it. Okay. Thank you.
Yep. Bing?
So for the master theorem, if we write A equals what, B equals what, or D equals what, these letters can be assumed, right? We don't have to redefine what A is, what B is. Like, there is no explanation required for these things, right?
Yeah, we know what A, B, and D equals. Yeah.
Okay. What's the letter used for the exponent on the log component? Oh, well, it's usually only used in the extended master theorem, but is there a letter for that, or we generally don't deal with
I think the log component is in relationship to B and A, right? So it should be one of those.
No, I'm talking about so it's in the second part, not on the left part, but on the right part, where it's O n times n to the power of D and log n to the power of what? That exponent.
I mean, you don't really have to. You don't actually have to give that a variable, right? That's just the work, right? So you can just say my work is O of n squared, and that's fine. You don't have to be like,
oh, okay, just write it out.
Okay. Yeah.
Okay, see, thank you.
Yep, no problem. All right. So the divide and conquer algorithms that we care about in this class are okay. Sorry. So what is a divide and conquer algorithm? What do we consider to be divide and conquer? Okay. And so the general approach is that you want to break a problem into several smaller parts. Okay. These are your subproblems. Okay. And then you want to solve each part independently. Each part can be solved by itself without relationship to others at the base level, at the smallest level. You can just kind of solve for itself. And then while you're doing that, as your solution bubbles back up, or as your solution goes down, you want to either eliminate work, merge work, or cancel out work. Okay, and this is the conquering part of it. You don't want to be where, if dynamic programming, right? The idea is I'm trying to solve every single subproblem so that each subproblem leads into the next subproblem. Divide and conquer is actually to try to do as few subproblems as possible, either by saying, yeah, I only need to work with this half because I know the first half is completely unneeded. That's binary search. Or, rather than constantly try to compare everything, I go, okay, well, if I compare smaller and smaller pairs, I can bubble that up to the top by merging them. That's merge sort, or trying to cancel out work. Well, I know that when I separate out all the equations, some of this math is going to be duplicated, and then I'm just going to do it one time, and then I don't have to do it over and over again. And that's the fast integer multiplication. So there's different ways of eliminating work, but ultimately you're trying to do as little work as possible when you go into a divide and conquer approach. And there is recursion to this, right? Like you are trying to, you are running the same helper algorithm, if you will, over and over again on either smaller and smaller parts or the larger and larger parts. So that you just at some point you're saying, okay, well, if I have this subpart of my overall problem, I do it, over and over again, I will get to my solution. And why is this effective? Why do we do divide and conquer approaches to solving problems? The thing about divide and conquer algorithms, and you will actually see this when you get your homeworks and exams graded, is that coming up with a solution for most divide and conquer problems is actually very trivial if you don't use divide and conquer. Trying to find the kth number in an array of numbers is actually pretty trivial. Trying trying to find if a number exists in an array is really, really trivial. And multiplying big numbers, in fact, like it might be really slow, but it's actually also trivial to just kind of multiply it up. The whole point of divide and conquer isn't to really find smart ways to solve a problem. Most of those problems can be solved by brute force. The thing about divide and conquer is to try to find optimal or efficient ways to solve the problem. So we care much more about efficiency during this section than we did a dynamic programming. Dynamic programming, the difficulty is to just solve the problem to begin with. That's why you sometimes end up with an O of n squared solution. Like, it's not super fast, but that's the best way and the only way maybe to solve the problem. Whereas divide and conquer, all of n squared, like, they are brute force ways to solve just about anything, but we're looking for something better, something faster. So reducing work through eliminating a portion of the input is effective because you don't have to solve for the entire input. Reducing work through eliminating redundant work, such as merge sort, is effective because you don't have to make every single comparison. You just have to make log n comparisons, right? You do n comparisons. You only have to do like log n times, whereas like a bubble sort is O of n squared. You compare every pair, and that's inefficient, right? And then you can do reducing through math, because math has certain properties where you can eliminate work. So fast integer multiplication is an example of this. FFT, fast Fourier transform, is also an example of this. This is not required material for this semester. You're welcome to go watch the lectures and read it in a book. It's a fascinating algorithm. So I think it is important to know that it exists and what it does, but you don't have to know too much about it for the exam. Okay. So yeah, if dynamic programming is solving problems by solving small subproblems, divide and conquer is solving problems by avoiding smaller subproblems. So the classic divide and conquer algorithms are your binary search, your merge sort, your fast select, your quick sort, your quick select, and your fast multiply, and your FFT. Now, the lectures are going to mention quick sort and quick select as divide and conquer algorithms. They are divide and conquer algorithms. You should not use them. They are mentioned as an example and how we can improve upon them. So quick sort is improved upon by using merge sort. Quick select is improved upon by using fast select. Okay. So do not use these, or else you're going to ruin your overall runtime. Okay. So that's important to know. All right, any questions about what divide and conquer algorithms are and why they exist and what the reason we use them are? Okay, Ravi.
Yeah, Joves, thank you for mentioning that. I want to ask something. While we're making our optimal divide and conquer algorithm, is it okay that we can do anything reminiscent or similar to fast select? Because the lectures had mentioned fast select, and I was thinking that if we need to use it, provided that we can justify it, then we can use something like fast select.
Yep, you can use any black box that is provided to you in the list that we have in the class, and fast select is certainly one of them. So if you need it for any reason and you want to use it as a black box, then feel free, go right ahead.
Okay, because fast select involves partitioning the list into many different partitions. So I just need to know that.
Yep, certainly.
Okay, thanks.
So a student asked, is fast select the median 2.4 section in? Okay, so there's some confusion with the way that some of these things are named. So I will go over it real quick. So median of medians is a way to particularly look for a median of a array. It is a well-known algorithm, and you should understand what medians of medians is. What fast select is using that median of medians as a pivot strategy. So the reason why quick select and worst case is O of n squared is that you don't have a pivot strategy. You're just picking a pivot at random, and that pivot could potentially be really bad if the pivot is at the end of one of your at the the largest or smallest of your array, and you're trying to pivot around that randomly selected pivot, you end up with a really bad runtime. So what fast select does, which is sort of, I think, named by Dr. Pagoda. I don't think like fast select is a well-known name of the algorithm. I think most people just say quick select with a medium or median pivot strategy. But we call it fast select in this class, so feel free to just use that. And the idea is, rather than picking a pivot at random, we use a much smarter strategy to first pick the median of of your array as a pivot. So that's O of n to find it, right? And then using that for your select strategy ends up making the overall runtime O of n. So it's actually a pretty neat approach to it, but that's why the naming is kind of weird. Okay. Yeah, and Tim has said that the lecture on fast select is equal to selection in DPV, but in DPV, I don't believe it's going to be called fast select. I think it's just a selection strategy that uses picking your pivot. Yeah, worst case, random can be open squared. It generally isn't, but if you pick a bad pivot, it can be open squared. And the thing is, so this is actually pretty key to how runtimes can actually kind of work in the worst case. Your different parts of your internal to your algorithm can be faster than the internal parts of other algorithms, but the overall runtime is what we care about. So picking a pivot at random is certainly faster than picking a pivot smartly, right? But because picking a pivot at random, even though fast, could potentially blow up the runtime of your entire algorithm, it is better to pay the cost of picking a smart pivot in O of n to ensure that the worst case scenario is O of n for your fast select. Whereas picking the random pivot of O of 1 could potentially blow up the runtime of the rest of your algorithm, which is bad. So strategies to providing a divide and conquer solution. Just like I said, in dynamic programming, you try to recognize patterns. Same thing in divide and conquer. You're trying to see what the input tells you about trying to figure out what the correct solution is. If the array given to you is sorted, it's a good indication you probably want to at least consider binary search. Binary search works on a sorted array, and so if the array itself is sorted, that's sort of like, ooh, can I do something with binary search? Okay. Consider modifying your target. So the target is set in binary search, but you can make it dynamic. You can change your target at each occurrence. You can decide, oh, I'm not actually looking for X. I'm looking for something related to X. So consider modifying the target. Okay, consider modifying the branching logic. You don't always have to branch half and half. You can branch 2/3 and 1/3. You can branch in different directions. You can branch, with always including midpoint, never including midpoint. There's different strategies you can change based on what your problem is trying to solve. And if the input is unsorted, right? If you are given unsorted input, you're probably not going to start with the idea of using binary search, but you can consider sorting it first, okay? But be careful with this, okay? You don't always just arbitrarily want to go, oh, it's unsorted. I definitely want to sort it. O of n log n is my runtime, because that's not always the case, right? If you think about fast select doesn't first sort the array in order to find the kth element. If it did, fast select itself would become O of n log n, and that's inefficient. We can do better. We can do an O of n, right? And so that's you only want to do sorting if you think sorting is absolutely needed. Otherwise, consider fast select or other ways of dealing with the array without sorting it first. And one way to really think about this, right, is if I asked you, fast select looks for a kth smallest number. But if I was to ask you, find me the largest number in the array, if your initial thought is, oh, I'm going to sort it first, that's a terrible idea, right? Because you can find the largest number in a scan of O of n easily, right? You just keep track of what the current largest is, and you just keep going until you find the largest. O of n, that's all you need. You don't need to do the sort first. Fast select is a much more complicated algorithm than finding the largest, but it kind of works in a similar fashion that you don't have to sort the array first if you're just looking for that number. Now, it could potentially, you know, you have to make considerations. If I'm looking for like, you know, K numbers, right? Maybe the trade-off of sorting it first so that all your lookups are all of one is makes sense. But it also might be, you know, okay, well, if K is clearly smaller than N, you know, or in some cases, you know, maybe, I'm sorry, if K is clearly smaller than log N, then all of Kn might be okay, right? So you have to make judgment calls and compare these runtimes to each other, right? So keep that in mind. Consider modifying the merge logic and the merge sort. So, you know, rather than doing a full sort and then trying to do what you want, you can do it as you're merge sorting, and then you can assume that everything you're working with is sorted on the way up. And maybe instead of just doing a merge, you eliminate some work completely, and then actually the problem gets smaller and smaller on the way up. So that's also a consideration. If you are working with fast select, consider modifying the partitioning logic, right? You're partitioning based on everything, you know, less than equal to p, equal to p, greater than equal to p. There's a potential of, you know, changing that to sort of fit what your problem is requiring. So that's one consideration. Other dynamic, divide and conquer algorithms consider. The fast multiply or FFT if it's math based. If it's really heavy math based and you're trying to do some, you know, multiplication, consider fast multiply. There's also a tournament algorithm. This is I don't believe it's covered in the lectures in the books, but it is something that you should, you know, look into and understand, because it is something we consider is simple enough that you could come up on the fly. So tournament algorithm, you just basically write your own. The idea is that you pair things up arbitrarily, and then based on those pairings, you start to eliminate things as you move up, and then at the very top of your tournament algorithm, you're left with like, you know, 1 or 2 or 3 candidates, and then you know, check those candidates for if it fits the problem that you're trying to solve. Okay, and so that should be it. Any questions on divide and conquer strategies? Ravi?
Thank you, Joves. I have a question about modifying the partitioning logic to fast select. Forgive me if I missed this or this has been discussed already. Isn't it going to cause a high runtime, like a really big runtime, such that we could make it more efficient?
It depends on what the modifications are, and it depends if it's needed. There are some situations where, you know, if you accidentally modify it in such a way that your partitioning becomes inefficient, that could hurt you on the algorithm. But there are situations where you might just have to, right? Like if there's a possibility that I want to go modify binary search, but both sides based on that midpoint is important to me. And so my binary search now no longer becomes O log n, and might become O n log n. Like, it's okay to modify a black box and end up with a larger runtime if that is what's required to solve your problem. We don't strain you to say, okay, if you use merge sort, you cannot go above O of n log n. If you use binary search, you cannot go above O log n. It really depends on the problem and what you're trying to solve.
Okay, I mean, what I really mean is like, isn't risky though, because risky because that could cause a suboptimal solution. I mean, we don't want such a solution.
I mean, nothing's risky if it solves your problem, right? Like, if it's the correct strategy and it's the correct answer, you can't just say, okay, well, I refuse to use it because I don't want to, you know, mess with the runtime. Like, if that ends up what needs to be done, that ends up being the right approach.
All right, thanks.
Karishma?
Hi, can you hear
Karishma,
me?
you're muted. Yes.
So can you re-go over the modifying partitioning logic to fast select? I wasn't quite able to grasp that. Sorry.
Yeah, no problem. So the partitioning logic of fast select is that you create 3 buckets to put your you know, answers into. You put one into the everything that you first find it pivot, and then you put everything into less than equal to p, you put everything into equal to P, and you put anything greater or equal to P, right? And so those are your 3 buckets. And so one such modification might be, I don't care if something's equal to P or less than P. I could potentially put everything into the less than equal to P and everything greater than P. That is one possible modification. Or you can say, I don't care if I care about the magnitude of how something is different compared to P. So maybe I'll make 5 buckets: everything less than equal to P minus 10, everything less than P minus 10, everything less than P minus 5, and so forth and so forth. So like you can do different things to the partitioning logic depending on what you're trying to find.
Okay, thank you.
Aaron?
Hey, thanks, Joves. So would we always be given a target runtime or no for the exams?
You will not always be giving a target runtime. In fact, I would say it would be rare for you to get a target runtime.
Got it.
Part of this class and part of designing the right algorithms is to be able to recognize what the correct runtime should be for a given problem.
Got it. Thank you.
Yep. Right. So one other strategy I should have added, and I'll try to add it in my do I have it in this? I can't remember the full lectures, but one thing to consider is that whenever you get a problem, first consider what the worst case is. First, consider what not the worst case, consider what the brute force solution would be, right? So if I'm trying to find the case, if I'm trying to find something in an array, it takes O of n to scan the entire array and find my my element, and that's it, right? That is a simple O of n solution. If we give you a problem like that, we are looking for something better. We're looking for you to do something better than brute force. So if you give us a solution that is equal to or worse than brute force, no matter how correct it is, no matter how divide and conquer it is, you're going to lose almost all your points. It is a gigantic penalty to give back a brute force runtime. So that's how you want to consider. You want to consider, what is my worst case? No, sorry, I keep saying that. What is my brute force runtime? I need to beat this. Okay. If you don't beat that brute force runtime, you're going to be in trouble. So one such thing is like, in O of n squared sorting solution. If whatever you're trying to accomplish is O of n squared by just doing like a brute force sort, it's probably not right. Okay, so recognize what the brute force is, get better than that. Now you can lose points on suboptimal solutions that is better than brute force. So we generally have a scale. We say, okay, we have a target runtime that we want students to recognize and be able to get. That is going to be full credit in terms of optimization. There could be better runtimes. There could be potential where there's a better runtime, but it's extremely difficult or extremely nuanced for you to get. And generally the TAs will talk about it and be like, how fair is it for a student to find this optimal runtime? Do we think that it's obvious? Do we think that it's a TA, most TAs looking at this problem would arrive at that target runtime? Then we go, okay, that is where we want to measure our students by. If a problem has maybe 1 or 2 of the TAs are able to find the absolute optimal, but all the other TAs would find a slightly suboptimal, then that doesn't seem fair to be like, okay, we want students to hit that runtime as well. So there's a target runtime. There's a brute force runtime where we go, okay, if we look at this problem in a very naive way, what is this runtime that we would achieve? Now, we've had arguments with students where students say, oh, well, I could come up with an even worse runtime than that. Therefore, my runtime is not brute force. That is not how it works. You can always make something slower and slower and slower. There's no limitation to how slow you can solve a problem. And so for every student that goes, oh, I got a brute force penalty, but I can actually go slower, that's not a good argument at all. Okay, so we have what we target as, okay, this is the naive approach, naive runtime. This will get a lot of points off. Somewhere in between is where we have some leeway. We go, okay, well, we really wanted an O of log n solution, but O of n solution isn't that bad. We can give, we'll take a penalty, but we won't take that much. A O of n log n is pretty bad. We'll take out some penalty. O of n squared is really, really the brute force that we think it is, so that you're going to lose all your points. So there's some leeway in between, but there's always a target runtime that we want students to hit, and there's always a brute force or naive runtime that we consider to be anything below this, anything this or below is just going to lose a ton of efficiency points. And that's how we grade runtime, well, the runtime of the algorithm in this class. So again, strategy is figure out what the brute force would be, beat it as much as you can within the time limit with the correct algorithm, but always beat it, because if you don't beat it, you're going to lose a lot of points. I would say it's better to approach, and students will also argue this with us, is like, hey, I have a working solution, even if it's really, really bad and it's brute force, why did this other student get more points than me, even though they have a better runtime, but they made enough mistakes, their solution will be technically wrong. It's two different grading scales. You start off with what your runtimes are, and that chunk of points is taken away. You cannot get those points back no matter how great the rest of your solution is. And then there's the rest of the points where it's like, okay, how many mistakes do you make? Okay, that chunk for brute force solution is huge. So the moment you lose that chunk of points, you will not be able to really make up for it, even though your solution is super correct. Because to us, a brute force solution that's correct is naive and not interesting. A second student recognizes that the brute force solution is bad, tries to go for a better, faster solution, and makes some mistakes along the way, but those mistakes might be minor, right? They might, be off by 1 or 2. The return value might be wrong, but they're starting to lose small points that could accumulate to being very bad if their solution is truly bad. But if they make a few mistakes here and there, but get an optimal solution, they're going to end up losing less points. So that is the strategy you should consider. Always be brute force, and then try to get the best solution you can once you get past that. Right. I know that was a lot. So if anybody has questions about that particularly part, Vikash?
Yeah, so one question I have is, if we come up with a solution which is better than brute force, but it's not the perfect solution because there might be edge cases that it doesn't cover. Obviously, we'll try to test some examples, but none of those are the edge cases. How would that impact the score?
You're probably going to lose a few points, but like I said, the penalties for that tends to be like -1, -2, right? They're not going to be like minus like massive amount of points. They're not double-digit penalties normally.
Okay, thanks.
Yeah, but if you make a lot of mistakes, it can add up, right? Like if you're like, well, my target isn't right, my branching strategy isn't right, and my final return value isn't right, but it's all log n, therefore I should get all my points, and that's just not the case, right? Like if your solution is completely broken, you may just get as few or fewer points than brute force. It just depends on how bad it is.
Yeah, and the only reason I'm asking that question is because the homework problem that we have, I came up with a strategy, and I think a few other students also, which looks good and is not very different from the right solution as well, the BIGO timeline. But the first solution is basically, there are edge cases that would not work, basically.
Yeah, I know. Unless I see those solutions, I won't.
Yeah.
Like I won't even be able to tell you how it's graded at this point. There's other TAs that's in charge of all the grading rubrics, and so I just have a general idea of what these penalties are. But the TAs like spend a ton of time going over the rubrics. Like several TAs will go get together and say, okay, I think that this penalty is a bit much because it's such a common penalty, or this penalty is not enough given how badly it breaks it. So there's a lot of there's a lot of collaboration and a lot of calibration that goes into grading. So I have no idea what that would be graded like until it comes out.
Yep. Thanks.
Mehitam?
If I'm not mistaken, if I heard you correctly, you said if you ask the k's largest, element, it would be like we can just use scanning. So I thought I heard you say that.
You can't no. So if you're looking for the largest number or the smallest number, anything that's the kth largest,
I mean, my thought was like you would just use a modified
kth
fast
largest.
select.
Yeah, kth largest is just, it would be fast select and open, doing simple like the brute force of what's it called? Kth largest to me would be sort it and then just return the kth value. And so brute
Gotcha.
force for me for kth largest is O of n log n.
Gotcha.
You get anything, if you get O of n log n or worse, you're gonna lose all your points, because that's like, that's like, if I can explain to you the solution in one sentence, it's probably not the solution we're looking for, right? Like if I say sort it, return the kth element, that's not really interesting solution, and it's also really, really slow compared to O of n, so not great.
Got it.
Okay. All right. Any other questions? All right, cool. So the solving recurrences part, this part I am going to go over very quickly, but there is a huge post on how to solve recurrences. If you have any questions or if you need help, go to that thread. There are TAs that will monitor that thread. There's other students that will chime in. So absolutely, if you are not sure about solving recurrences, go to that thread. So the first thing we care about is that if you're using a black box, really simple. Just say my black box runtime is this, and I modify this, which changes or doesn't change the runtime, and therefore my runtime is this. That's the simplest like level 1 runtime analysis you can do. The second part is to use the math. There's different things that you can do, but master theorem is the core of it. Okay, so what you want to do is you want to set up A, B, and D part of this equation. You need to explain to us what the A represents in your algorithm, what the B represents in your algorithm, what the D represents in your algorithm. So, okay. A is the number of recursive calls. So once you break down your subproblems, how many calls are you making to your function or your recursive function? B is the size of a petition in each recursive call. So this might get smaller and smaller. It might get smaller by a factor of n over 5, n over 3, n over 2. In general, your subproblems should be getting smaller in some way because you want to be doing less and less work. If your subproblem is growing, and by the way, recurrences aren't specific to divide and conquer. It's not that you can only establish a recurrence or only calculate a runtime using the math theorem on divide and conquer algorithms. It can be for other algorithms. We just use it for divide and conquer because it is the most relevant way to do this, right? So if your subproblem is not getting smaller, you're not doing the dividing part of divide and conquer, and your solution is likely to be going the wrong way. There are algorithms where, for whatever reason, the partition gets bigger and bigger, and that is a valid solution and a valid runtime in some cases, but probably not for divide and conquer, because the whole point of divide and conquer is to make your subproblems smaller and smaller. N to the D is the effort at each recursion. You can look at the D sort of like separately, or you can look at this entire term together. You don't have to say like, oh, my D is equal to 1 because it's an O of n work, or my D is equal to 2 because it's O n work. You can just say it's O of n squared work, it's O of n1 work, it's O of n cubed work, it's O of log n work, etc. Right? So you can try to look at this term entirely by itself. Okay, so then once you have your equation established, you can solve it in a few ways. There's the master theorem where you go, okay, well, I can take my different values and I can compare them. And by comparing them, it gets me to a runtime that I can claim. Okay, so if D is greater than the log B of A, then my runtime is O of n squared. Okay. If D is equal to log B of A, then it can be, and this can be simplified to this at the end. Then your runtime is O of n to the D times log B of n. Okay. And then if my d is less than log b of a, then my solution is n to the log b of a. Okay. And that's basically your three possible outcomes. Now remember, this d, sorry, could be 0. Okay. All of one work is valid, and in this case, d is equal to 0. Okay. So you can use that in, if this could be the case here. I think it's typically this case right here. Or actually, I think it's typically can be this case. So if your d is equal to, if it's your is equal to here, this could be n to the 0, and then this can be potentially log n. Okay. All right. So those are your three cases for your master theorem. If this looks scary to you and you don't like using this and you don't like memorizing this, you can also use substitutions, which in lectures I find substitutions to be very difficult to understand. Some students find it much easier. It's up to you. There's also another process we like to dub Christian's method, because Christian's the one that wrote the post. Originally, Christian is a head TA that's no longer with this class, but we keep our memories of him intact by saying it's Christian's method. I don't know if we actually call it Christian's method in the post anymore. Sorry, I'm trying to find Yeah, conceptual approach to solving. Oh, it's still called Christian's method. Great, I love that. Okay, so Christian basically sat there, looked at this equation, and said, "God, I hate remembering this." So he reasoned out what the equation actually means in terms of logic, right? So what's basically it's saying is that if this work is what is truly dominant of this entire equation, then this is the runtime that ends up being what we care about, right? And it makes sense. Like if something takes a certain amount of time to do, and this term gets dominated from it, we know that this term is going to be what ends up mattering. Likewise, if this term dominates this term, then this is where all the stuff is happening. How many subproblems I have determines how much work, mostly because this is all of one. If this ends up being all of one, you end up entirely dominated by how many subproblems and recurrences you end up creating, and that's your runtime. And so you see here that if let's see. Yeah, so if the d dominates the log b8 term, then all I really care about is here. Okay, that's what that's saying. If d gets dominated by this recurrence, then all I really care about is how long this takes. Okay, and then there's a situation with the equal, so you need to consider both. So you add two terms together. That's basically what the logic behind the master theorem is, and how that comes to be. So if you don't like using the master theorem directly, go read the post, understand Christian's method, understand his logic and his argument between why they work. And there's also a lot of examples of how you can use this. Okay. Any questions about solving recurrences, Aaron?
Thanks, Joves. So this, so the master theorem, it seems to lend itself to divide and conquer algorithms. Are there any other? I was doing some reading and I kind of came across another form of it for subtract and conquer problems. Would that be okay to use as well to maybe like solve some recurrences that take that form instead?
You need to establish the master this equation based on our class. So if you establish this this equation and then solve it however you want with any one of these methods, we don't care which method you use. You may not even use a method. You might just recognize that, oh, I know what this equation equals, and just give us the solution to that, and you're fine, right? You might just recognize the binary search equation. You might just recognize the merge sort equation immediately go to all of log n or all of n log n. That's fine. Whatever you do in between doesn't matter to us. But you do have to at least establish this equation.
Got it. Thank you.
Okay. Any other questions? I think that's my last slide. Oh, no, I have common mistakes, just like I did for dynamic programming. Now, these are common mistakes I've seen throughout the life of the class. These numbers have changed over the semesters, so don't put too much weight into like the actual percentage. Just know kind of the relation which mistakes are more common than others, and try to avoid the common mistakes, but definitely avoid all the mistakes if you get. So suboptimal solution happens quite often. Students go in, they think, oh, I'll just give it a correct solution, and I will get if I don't come up with an optimal solution, I'll at least get 90 on this problem, 80, 70, 60. It's much less than that. If you come up with a brute force solution, you are way off. You need to come with at least an attempt at a more optimal solution. You will see this penalty when homework 2 gets released, and you will see how massive that penalty is. Do not ever use if you don't beat brute force, you will get a very large penalty. Oh, sorry, I missed one. So suboptimal solution is just generally being suboptimal. This is different depending on how suboptimal you are and how hard we think that suboptimal solution is to get based on the question. Not beating the brute force is a standard penalty that is very, very large. So no matter what, this penalty stays the same from problem to problem. And we just say you gave a very naive solution, wasn't even worth writing, you're going to lose a lot of points. You'll get some points just because you made an attempt, but in general, if you're not going to get enough points doing this on every problem to pass the exam. So I would say don't even use this as part of your strategy. Always try to find a better solution than brute force. For the algorithm part, missing or incorrect base case is pretty often. If your recurrence has nowhere to stop or your base case doesn't give back the correct stopping conditions, you're going to lose points for it. The recurrence of splitting lacks details or incorrect. So this is, like I said earlier, not many students fall into this penalty, but when you do, it is a very big penalty. This is not a small penalty. So do not just give a one sentence algorithm thinking, oh, the TA will understand what I mean. Lacking details is a really bad thing to have on your grade. Well, on the justification of correctness, you have to explain to us why your algorithm, if you change it, why it branches a certain way. If you change the branching strategy of binary search, it's no longer a part of the original black box. So for that, you have to say, I branch to the left under these conditions because I branch to the right under these conditions because. And generally, this takes on the form of, I branch to the left because I know everything on the right cannot be possibly the right answer because of the following reasons. I branch to the right because I know everything to the left is not a possible solution because of the following reasons. Basically, that's how binary search gets explained to you. So explain it back to us under your conditions that you have set up. Does not mention array being sorted allows for use of binary search. This is such a big problem for students that they, it's so obvious I'm using binary search because the array is sorted. Guess what? That is an explanation of why you use binary search. So if you skip it, you're going to lose points for it. So you absolutely have to tell us why you chose black boxes under certain conditions. If you miss it, even though you think it's obvious, you're going to lose points. So try not to do that. I don't think this is actually a very big penalty. So the thing about these percentages is that even though this looks like 25% and this is 5%, so it looks like this is so much worse. This is a huge penalty, and this is sort of like a tiny penalty. So you do lose points, but you don't lose a lot of points. But if you make enough of these mistakes, they will add up. So be wary of that. And yeah, it's just how it ends up. On the runtime analysis, you are correct, but you ignore the black box modification analysis. 10% of students tend to do this. You make a small, tiny modification to binary search. You forget about it by the time you get to the runtime part, and then you miss it. Even if you do, instead of does my I'm terrible at writing with my mouse. Does my target equal my A of midpoint, right? If that is how binary search works, if you do something like T equals, does my midpoint, right? Something as inconspicuous, as simple as that. All I'm doing is shifting my midpoint by 2 to check for my target. That is a modification. your modification, obviously, to you and me when we're looking at this is all one. You're not doing much more, right? But you have to state it, okay, or you're going to lose points. So any tiny little modification that you make, you have to state how that impacts your runtime. Whether it does or it doesn't, we will still take points off if you don't mention it. Okay. Any questions about common mistakes? Bing?
Yeah, I have two quick questions. One, I assume the percentage in the parentheses are the percentage of people or students in the past making such mistakes, right? It's not a points being deducted.
Correct.
Okay.
Correct. It is the number of times when we do the grading, we have access to the statistics of which penalties were applied and how often. And these are the penalties that I see get higher than 1 or 2 or 3%. Like these are penalties I think like students regularly make that if I tell them ahead of time, they may not make these mistakes.
See, thank you. The other thing is last week when we did dynamic programming, you said the breakdown was like 262 for 3 parts. Is that similar here, or the algorithm is significantly higher in this case?
Let me take a look what the breakdown is. I think I know what it is, but I will double check because sometimes it changes, sometimes I forget. Oh, you know what? The rubric hasn't been set yet, so I don't know what the rubric will be. Tim, do you know what the breakdown of these 3 sections is? I want to say 216, 412, 4?
I do not know. I am not going to
Okay.
make a claim. We'll find out
Okay.
soon.
We will find out soon, and we don't keep that a secret from you. Whatever you see in the actual homework, so not the individual point values, because the individual point values on the rubric can change depending on how difficult we think certain things are. But the breakdown of how much is the algorithm part worth, how much is justification correctness, how much is the runtime analysis is worth, that will be you will see it on your homework if you submit, and if not, ask a student in the homework threads.
So I remember in the DP portion, you said even if your earlier steps were not so correct, but if your subsequent analysis and all those are correct, you can still get these points. But that's not a case for the DNSC, right? Especially if your solution is suboptimal.
I believe your runtime analysis is still tied to your overall algorithm. So whatever your algorithm is, you should say that's your runtime and why it is. Okay. So the runtime analysis to us is important that you recognize runtime, because in real life, right? Like when you're writing a program, like it's important to both recognize what you think the target runtime is, and that's the algorithm part. Understanding what how fast your algorithm should be, and we're looking for that in the algorithm part. There's also value in understanding how fast a algorithm is in general, right? If you know what the target algorithm should be, target runtime should be, but you're unable to recognize the runtime of your own algorithm, then you're not going to make that connection to say, oh, my algorithm is suboptimal. So there's value in analyzing the runtime of your own algorithm. So that's still stuck with it. Justification of correctness, I believe is tied to the actual problem statement. So if you justify the correctness of your algorithm to the point where oh, this is how it should work, and this is why the solution is correct, but you make mistakes in the algorithm, you'll lose points in the algorithm, but your justification of correctness could potentially be full credit. If your algorithm is very slow, but it works, and you justify why it works, and your justification is correct, you could potentially get full credit on both the justification of correctness and the runtime analysis. You'll just lose a lot of points in the algorithm. So we understand that these 3 parts are related, but we try to give you points where we can, such that it makes sense.
Thank you.
Yeah. Tira? I think you put your hand down. So Do students like it when I try to butcher their names, or do they just want me to stop? I can't tell. Like these names are really hard for me. I'm terrible at names in general. I don't know if students want me to keep trying, or if I should just like say your initials and go with that. So I'm gonna let SA decide if they want me to try to pronounce their name.
Yeah, so this is Sayed. Can you hear me?
Okay. Yes.
Okay. So quick question regarding the exam. Let's say in exam you expect us to come up with the divide and conquer solution to the problem, but we cannot think of any DC solution. Instead, we came with the correct solution, maybe even better timing, ON, or even worst case N log N, just like DC. Do we should, or let me ask you this, should we consider the other solution other than DC?
We work really hard as a TA team to try to make sure that the optimal solution to a certain problem is going to be a divide and conquer problem. I believe there have been cases where we accidentally let through some problems where a non-divide and conquer solution gets the same runtime. I can't think of a case where a non-divide and conquer solution got a better runtime. Not that I'm aware of. In cases where a non-divide and conquer solution gets the same runtime, we are still looking for the divide and conquer solution. So you should really try hard to get a divide and conquer solution.
Okay. So
And
just to clarify, we won't be getting any points.
you will lose a lot of points. But I will say, and I don't know if the TAs want me to tell you this, so I'm here to help. If your solution has some aspects of divide and conquer in there, that might be, good enough to get away with it. So like, if you find like say like a completely non-divide and conquer solution, and there's a it's like an iterative approach, it is optimal, it gets you the right solution, it's perfectly valid, throw some divide and conquerness into it, as long as it's not like oh, I divided it in two when I put it back together and it sounds kind of silly. Like it's not hard to inject divide and conquer solutions. Like even with the dynamic programming approach, I could probably find a way to put some divide and conquerness into it and still get the same runtime. So I don't know if that helps, but try that.
Thanks. No, that makes sense.
Okay. All right. Latera, LC.
Can you hear me now?
Yes.
Okay. I don't know if I missed this, or actually I did miss it, but in the justification of correctness, it says does not mention array being sorted allows for the use of binary search. So if we have a problem that says the input is a sorted array, we still need to state if we use the binary search algorithm that we're using it because the array
Yes.
is sorted.
Absolutely. Yeah. So if you have a problem that says given a sorted array, what do you do? And you go, oh, I want to use binary search, but I want to modify my binary search. Why did you pick binary search to begin with? That's important for you to tell us. You use binary search to begin with because the array given to you was sorted. On the other hand, if I give you an unsorted array and you want to binary search it, you will say, well, first I'm going to sort it with merge sort, and then I'm going to run binary search on it. Now, why did you run merge sort? Well, I ran merge sort because I needed a sorted array for binary search. Great. Why did you run binary search next? I ran binary search next because that allows me to find exactly what I'm looking for. So at each point where you decide on a black box, you have to tell us why that black box was chosen, and what the results of that black box does matters to your solution. So you have to tell us why.
Okay, thank you.
Yeah. All right. Let's see. Yeah, so there's a question in chat about, is it safer to use a usable divide and conquer, or and change it, or create our own? And Tim has a good answer, but I just want to emphasize this. You are given the opportunity to write the algorithm however you want. you are provided with the tools of black boxes to help you. If, for example, you decide, you know what, rather than writing out all the rather than saying merge sort, and then this is specifically what I want to modify, I think it's easier for me to just build merge sort from scratch and say each step exactly what to do. That's allowed. That's up to you. It might be easier for you to write, but I will caution you that if you do that and you don't state that black merge sort is the black box you are modifying, and you just run your own, homebrew version of merge sort, any mistakes you make writing that homebrew version of merge sort will be counted against you, right? If you don't correctly say how the left, when you're merging two subarrays, how the two comparisons of the leftmost element on each subarray works, or how what happens when there's a equal value from the left and right subarray, or how you decide the right subarray gets added to the new array, and so forth and so forth. Anything you miss on how a merge sort normally works, even if it's part of merge sort, but because you wrote your own merge sort, you're going to lose points for it. So it's certainly something you're allowed to do, but it is considerably more dangerous. Okay. All right. With that, I think my next slide is irrelevant for this semester. We will start covering some practice problems. I am going to give us a break about sorry, Bradley, question?
Yeah, sorry, I just thought of one, which is in some of the black box algorithms, and then in some of the lectures, we kind of mentioned that we could assume like array lengths were a power of 2 to avoid having to do things like ceilings and floors in both the algorithm and the analysis. Is it safe to kind of make those assumptions for solving some of these problems?
I would say that generally, powers of 2s, when it comes to like binary search and merge sort, doesn't matter. But there is potential when you do a modification that you can change that, right? So like if I was to do a merge sort and I am just running straight merge sort, when everything gets combined, it stays a power 2 all the way up. But in the problem, like say removing duplicates, as I am removing duplicates, you might remove 1, you might remove 2, you might remove 3, and so that kind of changes the number of subproblems you have, and you're no longer guaranteed a structure of a power 2 all the way up. I would say that consider whether that matters or not. In general, we try to just sort of be okay with it if it's perfectly understandable or easily easily ignored if it just works. But in the form of like some problems will say some problems you start off with even, and that matters, and then as you do eliminations or merging, you end up with an odd number and you don't know what to do. Like if I say for every pair do this, and I'm eliminating things as I do every pair, at some point I'm going to get to a level where I don't have every pair. I have 5 pairs and 1 extra element all by itself. In that case, you have to tell us how you handle that extra element all by itself, because for all pairs, what do I do with this element, right? Like that's not going to work. But if it's just like a binary search or a merge sort, I think you can easily, unless if you're not eliminating anything or you're not subdividing things into chunks, I think assuming that is a power 2 is okay. And in general, even when it's not a power 2, we try to provide you with the leniency to avoid that. Like I said, you don't have to tell us how mid is calculated for a binary search modification. We are okay with high, low, and mid. As long as you tell us what you do with that mid, then you're fine.
Gotcha.
Yeah.
So it kind of sounds like in many cases, yes, not in all cases, potentially. But even if you do erroneously, then there's a chance that the points you get off might be minimal in that situation as well.
Yeah, I mean, I would say that 1, if it doesn't matter, we won't care.
Right.
2, when it does matter, we try to allow you to be somewhat ambiguous about it by saying mid instead of telling us how mid is calculated. If it does matter, right? In terms of like, oh, I want to do this with
If
a
that's the
pair,
crux
but
of the
some person-
problem, yeah.
yeah, then you'll lose points. But even
Gotcha.
then, I want to say that we try to not make that penalty like half of your problem. Like it's not going to be something that's like, it's not going to be something hopefully you're going to get super mad about. It's going to be something you look at it and you're like, oh yeah, I understand why it matters and why I lost some points for it, and then you'll be okay with it as long as the rest of the problem is fine.
Awesome. Thank you very much.
Yep. Nishank?
Hi, Jovis. Can you talk about like when we would use merge sort versus fast select? Like, is it fair to say like we mainly use fast select when we need like the kth smallest or largest value in a list, and merge sort for everything else?
There's no hard rule to it, because the main thing is that when you're given a problem, it's not going to be like run fast select, be done, run merge sort, be done, right? Like problems like that aren't interesting for you to solve or learn to solve. What you're going to do is you're going to see a pattern of like, what this problem structure kind of looks like, and what would make sense. And I did go over that earlier in the office hours, saying, here are some strategies, and it's based on around the idea of like, okay, I see this input, I see what I'm trying to do. Can I use it? Can I not? But I will say that if you come up with a problem that either can be solved with merge select, with merge sort or fast select, fast select's faster. So if fast select solves the problem and merge sort also solves the problem, go with fast select. One specific case of this would be like if I'm looking for the kth value of an array, you could merge sort it and then return the kth element, right? That is a valid solution. Or I can then use fast select to find the kth element, right? The second use of the use of fast select is faster than merge sort. So in that case, I would go with fast select.
Okay, thank you.
Yep. All right. Now I'm really going to give everybody about a 2 to 3 minute break. I'm going to go get some fruit and use the restroom. So be right back. All right. Can everybody hear me? Hello, can you guys hear me? All right, great. So some early exam tips that I will go go back over when I do my exam prep office hours. I do recommend bringing fruit to your exams. You're allowed fruit, snacks, and drinks. I like fruit because it is something I can get some sugar into my blood. I can eat it without getting thirsty, and you drink too much water, you end up having to use restrooms. You don't have restroom breaks in exams, unfortunately, and so I just like to keep somewhat hydrated. I really like grapes. They're clean to eat. Cut watermelon's okay. You can have if you have a fork, don't try to eat it with your bare hands. I think cantaloupes are really good. Honeydews are good. Anything that provides something to chew to get your mouth damp, moist, I guess. um, don't suggest any sorts of fruits that like leave a lot of residue, like strawberries. I don't really like unless you eat it with a fork. Definitely not like blueberries that like get really messy. So yeah, just a quick suggestion. All right, let's go over the practice problems. So the first two that you see is 2.1, 2.5. I'm not going to go through these. They're really heavy on math, and I don't think they're like meaningful to like present in such a way, especially the first one. 2.1, there's a final answer, and then there's like a separate PDF that tells you how that answer is collected, and it's a massive PDF. Not massive PDF, but it's a massive tree. The thing that you should learn about the 2.1 is one, why fast integer multiplication works. Super important. Two, how to combine very small integers. You don't ultimately need to combine these giant integers or even figure out how that works. Let's just understand how what each of those subproblems are doing. You're not going to be given something like this during the exam and say, hey, work through this. One, because it's super error prone, and two, it would take up the entire exam time, and three, it's not very interesting for us to know if you can do arithmetic or not. Not that interesting anyways. So understand why the solution is, understand the small parts of the small subproblems, and that's it. 2.5 is mostly trying to use the master theorem to figure out a solution. So A, B, C, D, and E are really easy. Not really easy, but like they're meant to like exercise your understanding of the master theorem, where to put the certain variables and how to figure the answer out. F and G, everything below F are okay, maybe not F. I think F is actually okay. I think F is actually still kind of the master theorem, just a little complicated use of it. G and on, you use substitution for most of it, and some of it's logic. K is extremely difficult, but I would say understand how to do up to F is really important. You need to be able to apply the master theorem. Like even if you decide that, oh, I'm just going to use the black box or use black box for my solution, and then I'll be able to indicate what the runtime is. There will be opportunities where you are given a equation that you may not have come up with it, and be asked to solve for it. Be asked to get what the answer is. So be wary of that. And then we will start covering solutions from 2.16. So I think all these are Yeah, all these are sort of the written problems, and those are typically the problems I like to cover, is to go over what the written problems look like and how to reason through them. So let's go with that. Why is my Zoom so high? All right. So the problem statement for 2.16 is that you're given an infinite array, where the first n cells contain integers in a sorted order, and the rest of the cells are filled with infinite. You are not given the value of n, so you don't know when real number values end. So you can't just use n in trying to figure out, a solution. So you want to describe an algorithm that takes an integer x as input and finds a position in the array containing x. If such a position exists in O of log n time, okay, so your target is O of log n. If you have disturbed by the fact that the array A has infinite length, assume instead that it is of length n, but you don't know this length, and that the implementation of the array data type in your programming language returns the error message infinite whenever elements a of I with I greater than n are assessed. When this problem comes up, it's always funny to me to sort of go over some previous students' stories. I feel like that students look at problems like this, they understand it, and they make a good attempt at the solution. Then they get a solution that's either suboptimal or not quite correct, and they go back and find faults in the problem such that they can try to argue for points. TAs see through this, and it's not a good look or feel for other side. So with this problem in particular, I've seen students say they got it wrong, so they spent days arguing how an array can't actually be infinite. No matter what programming language, no matter what system, no matter what computer, an array literally cannot be infinite. And that is missing the entire point of trying to solve this problem, trying to understand this problem, and trying to understand an approach and divide and conquer. You spend those 3 days arguing something like that you are absolutely not going to get points back for, and you lose 3 days worth of study. So when you read a question like this, try to answer it the best you can, and try not to find like a situation where you have to spend days arguing with TAs about it. What happened to my? Sorry. Give me 1 sec. My thing is not. Why is this not refreshing? Please refresh so I can. What if I restart? All right, cool. All right, so the idea is that you have infinite array, that you cannot just simply go, oh, I'm going to just binary search it, right? Because hopefully you see this and you recognize that this is it's a sorted array, and there's a log n runtime, so it's probably going to be binary search in some way. Now, keep in mind, again, a student asked earlier, but we do not give you the runtime in most cases. Most of the time when we present you a problem, part of the difficulty of the problem is to actually find what that target runtime is by understanding what the problem is. And you should be able to recognize that even without it being told to you, right? So if we right, so if we got rid of this, right, what do we think the target would be, right? So again, I'll brute force, right? Open, right? I can take the beginning of my array and I can just scan it to the end to find I'm trying to look for x, right? So I can just scan it to the end. I can do that in n. No matter how big the array is, there is a given n cells that I know is sorted. And so all I ever have to do is search through n cells. It could be the very final number. That's fine. So it'll be all of n brute force. So now I need to consider, okay, I need to beat this all of n brute force. Well, merge sort certainly not going to do it, right? Fast select certainly not going to do it. So the only real option I have is binary search. And binary search is all log n. So in my mind, I already know what this target should be, is that I am looking for a log n solution. Okay. So you don't actually need to be given the runtime for this. Even before you start, even before you come up with a good solution, you should be going through this like logical stepping of like, okay, what am I trying to get to on my pack? And so in order to use binary search, what do I need? Well, I need a fixed size array. I need to have an n size array, and then I need to have a target to look for. What am I missing in this problem statement? Well, I have a target I'm looking for. I have the start of my array, but I don't have the end of my array, right? If I don't have an n, if I don't know what my n is, I can't start doing my high, low, mid kind of calculation, right? So then what I need to figure out is how to find the end of this array, okay? And hopefully you can see that if a binary search can take an array and make it make your search space smaller and smaller, the opposite of such an algorithm is true. I can start at a very small search space, and instead of having my big search space, I can double my search space to find what some endpoint to where I need to search. Okay, this turns out to be called either galloping search or exponential search. Those are not black boxes to you in this class, but it is a hopefully a well-known algorithm to some of you. And even if not, right, the idea should be something you can come up with. If you can have your search space, you can also double it. And so the solution we end up with is what's called a galloping search. So let's see what that solution looks like, and let's talk about it. Because I want to keep this in view. All right. So the solution you are given, you're told, well, we start with an index 1, and we double that index on each iteration. We continue until our whatever we find in the A of that larger index is greater than or equal to x. Right? We end when we have found some boundary that is above what x is. Okay. This efficiently finds an upper bound for our target value using an exponential search. Again, exponential search is in the black box, but that's what it's called. You don't look for n because you don't know what n is. You could potentially look for an infinite, which is fine because that it will still be bounded by log n in terms of worst case runtime. But really, you just need to find some boundary that's greater than or equal to x. Because once you find something that's greater than or equal to x, you can search below it to find where x is, if x exists, right? And so once we do that, we just perform a black box binary search from A to that index for the target value x and return the result of that search directly. And what this means is that if you consider what the answer here is, what the question asks here is, if such a position exists, right? So you would think, okay, well, I need to also say return x if such a position exists. You can. That is perfectly valid, and we would accept that. But you want to leverage what binary search does for you without you having to do much about it. And what does binary x do when it doesn't find x? Well, it returns none, right? It doesn't do any. It just ends and it tells you can't find it. What that means here doesn't really matter to us because we can just do the same thing. So that's why I like leaving out that detail because it's exactly what binary search would have done. Right. So then when we justify it, we say, okay, so the array is sorted, key detail, which allows the use of both the exponential search and the binary search. Okay. What is the exponential search? Well, we defined it in our algorithm. We call this exponential search. So array being sorted gives us access to both of these algorithms. By doubling the index at each step, we can deterministically find an upper bound that must be either infinity or a value greater than the target. Okay. We know the search with this upper bound must terminate because we exceed either the target of n or we hit infinity, right? Once we have the upper bound, we can leverage binary search as a now bounded portion of the array to find the target. So this part here is pretty key. It seems pretty throwaway, but this is required. The reason it's required is because not only did you choose to use binary search, and you have a reason to choose binary search. Next, I'm going to ask you, why did you have to do anything? Why can't you just run binary search to begin with? You can't run binary search to begin with because you have no bounded space to search through. And so in order to do that, you have to run the exponential search. So now that you've run exponential search, and now that your search space is bounded, now you have all the requirements needed to run binary search. So that last sentence is actually really important. Otherwise, there was no reason for you to run exponential search. Okay. Runtime analysis, this is just going to be a breakdown, doesn't use master theorem, which is fine. So one of the other thing is that even if you don't use a black box, if you want to avoid using the master theorem equation, you can also reason through the runtimes as long as it makes sense. Okay, so we're doubling the index at each iteration. We are exploring all 2 of I, a of 2 to the I, where I is some number less than the log of 2n. This results in log n, since the highest upper bound search goal is 2n, right? You can't go past 2 times n because there wouldn't be any reason to. You would hit a infinite element after n, and because you can't find n, your search space at max is 2 times n. Okay, and so to find that 2 times n, because you're doubling, your space is doubling each time, and therefore to find that 2n is log of that, so which results in log n. Okay, and so the known runtime of binary search is over n, since the bounded portion of the array is at most 2n elements. We haven't done any modifications to binary search, so we don't need to talk about it. And so our overall runtime is log n time plus log n, which gives us all of log n. Okay. Any questions about this solution and how we arrive at it? Awesome. Oh, Natira?
Yes. So I see the runtime analysis and it sort of makes sense. But what I'm not clear on is, let's just say I started with some value that wasn't exactly too I mean the smallest, right? I don't know. Let's say we did 4, or I don't know. And then I compared it to x. What is that not constant time? Because I'm just starting, like each search isn't constant time. Does my question make sense?
Your search of whether your A of I is equal to your greater than or equal to your x is a constant time step, but you are going to do log n of those steps. That's why you end up with a log n runtime on the exponential search part.
So regardless of where I start, or regardless of how I double or expand on that number, then it's still log n.
I mean, if you do a triple or quadruple, it might come out a little bit differently. That wouldn't really be, because whatever time savings you make by jumping further and jumping up at a higher scale or higher step, you have to pay the cost of that by doing the binary search on a much larger scale, right? Like if I'm doing 4x instead of double, I'm going to find my boundary a little faster, but that leaves me with a much bigger chunk of space to search for. So I don't think there's any cost savings there.
Okay.
The runtime might end up being differently depending on the calculations.
Okay, thank you.
And Junatha?
Question on the binary search that you're doing. I know that you're galloping to find the upper bound and then finally doing the whole binary search from 1 to A to the index, AF index. But if you keep tracking what was my last point, I think that would improve the final binary search, but the overall runtime is not really impacted. Does it really matter to do that?
No, it's one, it doesn't really matter because, like you said, worst case scenario, it's still the same. Two, you won't lose points for it. But three, if you do it, you kind of have to explain why you do index -1 instead of 1, right? Like it's assumed that whatever x is, once you find the upper bound, is going to be between 1 and that upper bound, right? So not much there. But if you do a of I -1 to a of I, you have to explain to me why it's between a of I -1 to a of I instead of searching the whole space, which is fine. If you want to do that, you can say, oh well, because we know that it was greater than equal to it was greater than a of I -1. That's why we searched to a of I. And now that we know that it's less than a of I, my search space is between a of I -1 to a of I, and therefore binary search on that works. And so that is a little bit faster, maybe not really. But if you think that feels better to fully explain that and you want to go that route, perfectly fine.
If I go that route, then what would be my final binary search runtime? It won't be login, but do I have to really derive that out?
It's still login, right? Because your
the upper bound, okay.
Right. It's your upper bound. Yeah.
Okay.
Because so what ends up happening is that you either get login normally, right? Or you end up with, okay, well, instead of actually n-1, right, to do so it's actually n-1, right? That's your search space, right? Your search space is n-1. Or you end up with log of n minus n over 2, because you now have to search between where my n is, where I find n, and half of that because it doubled, right? And so this gives us log n as a big O, and this gives us log of n over 2, which also equals log of n. So doesn't matter.
Gotcha. Thank you.
Yep. Georgie? You're muted if you're trying to say something.
Hey, can you hear me?
Yes.
Oh, sorry about that. Thank you. The question is, let's say the input was not sorted, and can we say we're going to use black box sorting algorithm without the upper bound, or we need to kind of do the same thing, go little by little, so to make sure we have upper bound and sorted, or just mention that we're going to use the algorithm for sorting.
So if the array wasn't sorted and the correct solution is to do sort in the binary search, one, you wouldn't be able to sort it normally because you need to know how to divide up the subarrays, and you don't know where the subarray endpoints are, right? If you were doing sort, but if you had to sort it, it's O of n to find the first infinite element. And since your sort is O of n log n, that O of n scan to find your end element is dominated by the sort anyways, so it doesn't matter. So just scan the array to find the upper bound, sort it, and then do binary search.
Okay, makes sense. Thank you.
Yep. Anika?
Can you hear me?
Yes.
Okay, so for that last part, so what didn't it say in the ed post, like if you have the first part and the second part are the same runtime, you multiply it by log n. So do you not have to do that in this case for the final runtime?
It depends. Like if if one runtime depends on, like if one runtime is multiplied out by that runtime, like if I am doing log n number of binary searches, I would do log n times log n. That's, because I'm doing one algorithm, which is log n, and I'm doing a log n times. Here, I'm doing one algorithm that takes log n. I stop. I start a second algorithm that takes log n. I stop. So I'm adding the two runtimes together. Whatever the runtime was to do the first part, and then the runtime to do the second part. They don't multiply out.
Oh, I see what you're saying. Okay, thanks.
Yep. Robbie?
Thanks, Joves. I just want a quick question. When I did 2.16, for one thing, on the correctness, I had written down the I hadn't mentioned upper bound, but I did say that mention subarrays in my algorithm incorrectness. Would that be acceptable? Or if I fail to say upper bound and when I mention correctness, am I going to lose points for that? I know I said subarray and explicitly explained that.
It depends on how your correctness is written out. Like if it implies that your subarrays are determined because you have found a upper bound, like even instead of saying upper bound, I said, by doing this, I find where the end of my subarray to search should be. Like you don't need the exact words upper bound, but in terms of finding a limitation to what your search space is important for this question. So it would have to be very clear on you are looking for the limitation, and this is how you find that limitation. Upper bound is just, words that can have alternate ways of saying it.
Yeah. I know the solution you brought up mentioned upper bound a lot, and I know I didn't mention upper bound, but I did talk about subarrays in my algorithm justification. Also, just one more thing, and I'll let you go on. In my runtime analysis, I didn't say all of log2n. I just gave the overall runtime analysis for for exponential search and binary search. And then I just went on to say what the final runtime was. Is that acceptable, or was I supposed to explain more?
You can say your binary search is all log n, and you can say your final runtime is all log n. In terms of your runtime analysis for your exponential search, it really depends on how you set it up. Like if I said, something like I'm looking for a upper bound to my binary search, there are, I would do no more. I'm searching for some constant of n, and it takes me log of that time to do. I could see like a potential of leaving out the 2n, but it really depends on how you describe it. I think in general, students need to take away from these practice solutions is that you don't need to get everything word for word, but you should get the general same gist and the same important parts, because this is what TAs are going to look for.
Right. I understand.
If you don't say log of 2n, it's okay as long as you make it clear that doing the exponential search breaks down to log of n in some way.
Right, and that's why I said I just said the exponential search takes log of n time to search for a subarray containing x. Is that acceptable, or did I miss anything?
I don't know what the rubric would be, but to me, I would want to know why it was log n, not just like it's log n and that's it. I would want to know why your exponential search takes log n.
Okay, so explain how I came to that.
Yeah.
Okay, thanks.
Because it's not a black box, right? So if it's not a black box, I need an explanation of it. Georgie? You're muted. I don't know if your hand's up from previously or if you have a question. Okay, I'm gonna skip you for a second. Come back to you if you're still up. Bing?
Hey, I noticed that in the algorithm, it doesn't address this, the infinity case, but it's explaining the justification, right? It says when you keep doubling, you will eventually either find a value greater than the target, or you'll be infinity, right? So is that the general expectation? Like we don't have to deal with those corner cases in the algorithm and just explain that in the justification, or should we actually do the opposite, try to have the corner cases explaining an algorithm?
First, I don't think it's a corner case. I think it's a very real situation that you're probably going to hit infinity if x is a number very close to the end of your array. But this right here covers that. The a of index greater than equal to x, infinity is in fact greater than equal to x, so it just covers it.
So that's why
but
you think it's not necessary to spell it out, right? There is no need to.
Yeah, I think if instead of infinity, we say, numbers are sorted until a certain point where the numbers flip to negative, right? Like if the number becomes -1, -2, -3,
right?
I would have to say in here, a of index greater than equal to x if positive or negative, and then continue on. The fact that infinity is covered by this equation is fine, but if it wasn't infinity, if it was a negative number, you would have to explain that situation.
Okay, that makes sense. Yeah, thank you.
Yep. I would not say that it's being ignored. I would just say it's covered by the general statement.
So it also means when you say infinity, you assume it's positive infinity, not negative infinity, right? Because when I first read infinity, I didn't assume there was a sign on it. So.
Yeah, we would tell you if it was negative infinity. So yeah, filled with the infinite symbol has a sign, and just like numbers, when there's a lack of a sign, it's implied to be positive.
Okay. So as long as it's not NaN or undefined, we can always assume if it doesn't have a negative sign, it's positive, right? So.
Yep. Okay, let's move on to the next problem. This next problem is majority element. This has two parts, and we will go over what is considered a easy and inefficient solution versus a more optimal solution. (2.23) majority element. An array A of 1 to n is said to have a majority element if more than half of its entries are the same. Given an array, the task is to design an efficient algorithm to tell whether the array has a majority element, and if so, to find the element. The elements of the array are not necessarily from some ordered domain like integers, and so that we can there can be no comparisons of the form a of I is greater than a of j. Think the array element as GIF files. However, you can answer the question in the form of is a of I equal to a of j in constant time. So one thing that students really get tripped up by this, which is kind of funny, but like happens all the time when I present the solution. They're like, what if, and what if this? The really key part here is more than half. A lot of students, when they design a solution to this, or wonder whether the model solution works, will say like, oh, what if it's I have 4 1s and then 2 2 3 3? That's not a majority. You actually have to have one more than half the entries. So that's a key thing to understand. And I want to point this out as sort of a cautionary tale when you go into these problems on the exam. Read the questions very carefully. Check your assumptions. You might think that like, oh, in my mind, I'm just looking for anything that has half of the entries, but you have to be very careful because the problem very much states more than half the entries. And if you make that mistake, it's a completely different answer and it's going to be wrong. So be very, very careful on first reading the problem statement fully, understanding it, and making assumptions, then go back and check those assumptions against what the problem statement is. Okay. So when asked if 1 1 1 2 3 would have 1 as the majority, right? Yes. Okay. So A is asking, show how to solve the problem in log n time. Again, you're not going to generally be giving a target runtime, but I think in this problem specifically, it's asking for 2 different solutions to sort of get you thinking, well, even when you hit divide and conquer solutions, some of them might be more optimal than others. And this is what I was saying with the way we grade, right? Like if I look at this, what's my brute force? Well, my brute force is to compare every entry with every other entry to see how many comparisons gets the highest number of equals, and then count that up and then see if that's greater than half plus 1. So if I have to compare everything, this brute force is all n squared. Okay, so this would be a huge penalty. Okay. Here it's saying, okay, well, can we do better? Can we do all n log n? We can. And if we do all n log n, which is not not the most optimal answer, but it is a better than all n squared answer, it will still get a penalty, but it won't get this massive penalty that you see for brute force. You just get a, depending on how easy or hard we think this suboptimal solution is. Okay. So hence split the array into two arrays, A1 and A2 of half the size. Okay. Does knowing the majority element of A1 and A2 help you figure out the majority element of A? If so, you can use a divide and conquer approach. So this is basically telling you, let's consider merge sort, right? You're splitting the array into two subarrays, and we know that if I have a majority on the left and it's the same majority than it is on the right, then that's my majority for those two subarrays, and I can bubble that up. If I don't have a majority on the left and I don't have a majority on the right, or okay, so if I don't have a majority on the left and I don't have a majority on the right, or my left majority and my right majority is different, then I need to keep track of what the most popular candidate on both sides is, so that I can later determine if the two sides combined can give me a majority. And the only one that can be a candidate majority of both sides are the two candidate majorities, right? So think about it. So if I have, right, let's just go with an easy example. I have 5x 4y, right? 5x is a majority here. And then if I have same here, right? The majority of both sides, if they are equal to each other, has to be the majority combined, right? So that's an all one check, okay? Real quick. Now, if all of our subarrays happens to do this, then we're good. We're done. We just keep bubbling this majority up, and the ultimate majority is the majority of both sides, right? But it could get a little tricky, right? If I have something like this. Right? If I have 10x 1y, actually I don't want 10x. I want what was I working with? 9? Right? And I have again, let's say 4x 5y, right? So now I have two separate majorities. I have 5y and I have 9x, right? So I don't know, right, from just this detail, which one's going to be the majority. Is it going to be y or x? I need to keep track of how many x's there are and how many y's are. And now I know, well, okay, well, I have 9 on this side, I have 4x on the other side, so that gives me 13, and then I have 6y, so that kind of gives me how many. But the only candidates that can be the majority overall are the two majorities from both sides, right? Because if I had a bunch of z's here, 4z, yeah. Need to keep another 4z. Yeah. No matter what, the z's are not going to add up enough to be a candidate for the majority. Okay. Now, there could be two possible majorities. But what's interesting is that if okay, when I have the situation, students are going to say, well, maybe x and z are both candidates for majorities because they both are equal to each other in the grand scheme of things. It turns out that because of this way this is set up, the left side actually has no majority, right? I have 9x, 9z, and 1y. None of them has the required number of 11. 19, yeah, 11 to get the majority. And then on the right side, I don't have a majority, right? 5y is no longer enough to get a majority. So because of that, I don't have a majority on either side. I have no candidates. Okay. But if I had, y as, much higher here, let's say okay. Y is still a candidate for being a majority, but yeah, together you end up with no majority. There's no majority on this side. Okay. So that's kind of like how it goes, how it bubbles up. You only ever need to consider the majority of the left side if they exist, the majority of the right side if it exists. You never have to consider too many candidates. And that is how we are going to lessen our number of comparisons on the way up. And that's how we get this this O of n. There's going to be log n, right? Your log n is very much like merge sort. You're splitting in two, splitting in two, splitting in two, getting lower and lower. The n comparison means I don't have to compare everything to each other. I just have a limited number of possible candidates. So let's take a look at this algorithm and see how it's written. Oops. I just hide my ugly handwriting a little bit. I often have conversations with my friends of like, giving up some skill or ability to trade off others. I think one of the things I would trade for is nice handwriting. I think I'd be willing to be a little bit worse at some of the other skills I have in order to get pretty handwriting. Okay, so our algorithm here is we first divide the input into equal size subarrays A1 and A2. When a base case of a subarray size 1 is reached, report that value as the majority element. Okay, so you are a subarray of 1, you are your own majority, right? If you have a town of 1 person, that person can vote however they want, and that person wins. At each level of recursion, you combine the results of the left and right subarray as such. Okay, so here's the rules of how we are going to combine. Check the majority elements from each subarray if it exists. Okay, for each majority element, count its number of occurrences in the combined array. Okay, if one of the elements remains a majority of the combined array, then report it as the majority element. Else no. Now, why is this important? So I said we can have at most 2 candidates ever to be a possible majority of the 2 combined subarrays. If we have like 3 or 4 candidates, if that is unbounded, this ends up being O of n times the number of possible candidates, because each of them could have equal share of all your stuff, all your majorities. But because we're only tracking 2, this ends up being I would need to verify the count for one of them, and I need to verify the count of another one. So it's O of n, right, times O1 work. Okay? Well, I guess O2 work, right? Because I'm going to take one candidate. I'm going to count how many. How long does that take to count that subarray? O of n, right? I compare to every single possible other candidates, other votes, and to see what did I call them? All the other elements, and see however many we have. And then we O2, and we do the same thing. Okay. Sorry, I know I keep saying vote and candidate is because this problem is generally used for a voting problem, but it is just majority element. So you compare to n elements on each potential majority, and since I can only have 2 potential majorities, I only do it twice, so it's O n. And then I do this all the way down, and so that gives me O log n, which is how many overall recurrences I have, how many times I split up, and that is multiplied by O of n worth each time. So this gives me O of n log n. Okay, and then let's go over the correctness. Oh yeah, and so once you're done there, If none of the elements, if one of the elements remains a majority for the combined array, then report it as a majority element. Else, no. Okay. So basically, you could potentially have subarrays that say, I have no majority element. So if I have no majority element, I have no candidates to present as a possible one to consider. Okay. So then when the recursion unwinds to the original array, return the majority element if it exists, else no. So anytime you compare against a no, then like if I have two subarrays and they both return no, then I have no majority element of the combined subarray. If one of them returns y and the other returns no, then y is the only one I need to care about. Because my y is my majority on the left, I need to see if y remains a majority when the two are combined. Okay, so this information keeps following. Okay, the justification of correctness by recursively dividing the input space, we can efficiently compute a count at each level of recursion to obtain the final result when the recursion unwinds. If a majority element exists at all, then at every level of recursion, there must be at least one subarray in which that element is also the majority. Okay? And thus the recursion unwinds, the majority element is guaranteed to be passed to each successive level. So it's going to bubble all the way up. We're going to have candidates, if there's a majority, go all the way up. Now, it turns out that if you have no majorities in all your subarrays, it's because they've been canceled out by another candidate. So every single candidate, every single time you have something that could be the majority, and it got canceled out by another subarray that could if they equal, right? If they equal, they cancel each other out. If every single recursion cancels each other out, there's no majority, right? Every single possible candidate has been canceled out by another possible candidate, and therefore there's no majority element all the way up, and so you're done. So the runtime analysis, each level of recursion, we have split the work into two halves, b equals 2. Okay, so this is where we use the master theorem, b equals 2. Operating on both halves, a equals 2, and performing all of n work, d equals 1, by counting the number of occurrences at each level. This gives us an recurrence of 2t times n over 2 plus O of n, which solves the O of n log n. Notice how there is no math. You don't have to show it. And it turns out when you look at 2t n over 2 plus O of n, that is exactly merge sort's equation. And so if you recognize that as merge sort's equation, you can also recognize that merge sort is O of n log n and just give us the runtime O of n log n. Yeah, and I think it's also nice that like if you were able to recognize that this is basically modified merge sort, and if you modify merge sort, you could actually present the solution as a modified merge sort, right? So like I can say we do a merge sort, but instead of actually sorting and merging two sorted steps, what I'm going to do is calculate a candidate majority, and this is what I do here, and then continue on with merge sort. And at the end, instead of a sorted array, I am going to have two candidate up to two candidate majorities, and I am going to check whether one of them is the majority or not all the way through. And if there is, return it. If not, return no. This is a modified merge sort. I have not done any. My work at each level remains all of n because I need to compare up to two candidates across n elements. And so I do all of n work similar to merge sort. Everything else remains the same. My runtime is the merge sort of all of them again. So that is another approach to do this, but you don't have to do it that way. You can also just explain your own algorithm as you go. All right, questions here, Jafar?
Hello. Hello, Joves. Thank you for your session first. Here I have two specific questions, please. So first of all, when I was thinking about this problem, I thought about a dictionary or a map. Okay, maybe to store how much is the majority on the left, how much is the majority on the right. Okay, and then start comparing it. But it's not the purpose of this question because, okay, it will add a little bit of OFM, but then at the end, I'm doing the same that what you are doing here because I need to compare the first majority with everything on the right and the second with everything on the left, which is basically n over 2. Okay, it's fine. It's not a big deal. It's still OFM. But the problem is here, my question is, if we are talking about a map or a dictionary, what is the complexity? Because I thought, okay, for the hash set, I was thinking about the complexity so of 1, but then I thought I understood that it is O of n. Also for the map, if we are using a map, complexity of adding and getting or searching inside a map, it is O of 1, yes, or it should be O of, O of n.
Any hashing type data structure in this class is worst case O of n.
Oh. Okay, so we can never use them.
Right. Otherwise, this entire solution can be done in O of n using just a hash map, right? You just hash the you
hash
the
them, you count
equation.
them, that's it. Yeah, O of n. But this but if you are considering it O of n, then it's O of n squared. So we cannot use it.
Right.
Okay.
If you were to use a hash map, it would be O of n squared. Correct.
Okay. Thank you. Thank you.
That being said, if you were to do this on like a leak code question or an interview, the general world outside of this class considered hash maps and hash has to be all one. And so that would probably be the correct solution in like a leak code type environment or interview question. But for this particular question, it is not. But in this class, in the textbook, it does not. The cache?
Hi. So there's one case here where if both sub-arrays do not have a majority element, it's basically no, that's O of 1. I believe there's another case where both sub-arrays have the same majority element, and you could just respond with that majority element without doing that ON work. And if you did that, it really doesn't change the overall timeline, but it is still better performance. Should we think in those lines, or is that not necessary?
Not necessary, and it again adds additional work to you. If you want to do it, that's fine. If you don't, that's also fine. We're always looking at the worst case in this situation, and the worst case is I don't know. I don't know between left and right which one the candidate is the correct majority, so I have to count. If you want to shortcut it at O of 1, it can be kind of dangerous in this class because one, it's additional things you have to write. You have to explain those cases. And then you might accidentally think that was optimal in the runtime at the end when it's really not. We cannot make that kind of assumption. So it does not impact the worst case runtime. You're just adding extra details, extra shortcuts, if you will.
Yeah. Okay. Thanks.
Okay. Latira?
So modifying merge sort is easier for me to reason through this, which is fine. But then someone asked in the chat, could you use fast select? And I think I can see how fast select would work, but then someone says it's not comparable. So if we did fast select and just didn't use a third array, would that work? Since we're only comparing the equals, so let's just say we picked a random value in the array and said if the value
I don't think so.
No,
I don't think so, because the whole point of fast select is that you are putting things into 3 buckets and then you're just getting rid of some bucket, right? You're trying to get rid of like, well, this bucket isn't going to be within my cake element, right? So you get rid of it because my left side has more than k numbers. My right side has less than k, n minus k, whatever, and then you just start going, down that path. What happens when you pick a random candidate, or I don't even know how you pick the candidate. Let's assume random, right? And you go, okay, well, this bucket has everybody that's in this candidate, and everybody has. So that would be interesting. You would do all. Hold on.
I was wondering about
it wouldn't work. Yeah. So
Sorry,
I'm thinking. Yeah. So I'm thinking about it, and I don't think you can, because what you're gonna end up doing is you're gonna split the buckets into 2. You're gonna have one that matches the candidate and one that doesn't match the other candidate. What's gonna happen is that if you're lucky and you pick a candidate that's the majority, your bucket of candidates that elements that match that candidate is going to be bigger than the other bucket, and bam, you're done. That's your solution, right? But what you're doing is you're eliminating possible candidates from the majority, right? And so if you every time you either find a majority or you don't find a majority, and then you're going to eliminate. What you're going to end up doing possibly is you try one candidate randomly and it only has one of itself. Then you're left with this giant bucket to go through. You pick a second candidate and it only has one of itself. You're left with this giant bucket to compare. And every time you do this, you potentially can only lose one subproblem, if you will, at a time. You're going to get to a n times n minus 1, and that is going to be all of n squared overall runtime. It'll work. It'll just be very slow. You're basically doing the comparison of saying brute force.
Okay, thank you.
Is how I understand fast select would work in this case. There could be potentially a different approach. Someone could write it up, and other students can look at it. But I'm not thinking of like another fast select candidate. The problem is that you can't compare to. You can't say less than equal to, greater than equal to. So you just end up basically with yes or no, and you're doing yes or no across all candidates.
Yeah. Okay. Thank you.
Yep. No problem. Nishink. You are muted if you are talking. Okay. Hopefully that's it. So there's a second solution that is more optimal, and we will talk about that. Now, the idea in for the second solution, let's put down the question first. Can you give a linear time algorithm? Here's another divide and conquer approach. Pair up the elements. Arbitrarily you get n over 2 pairs. Look at each pair. If the two elements are different, discard both of them. If they are the same, just keep one of them. Show that after this procedure there are at most n over 2 elements left, and then they have a majority element if and only if A does. Now, this is where I say that you cannot trust that the number of elements are going to be some factor some factor 2, because what happens is when you start to eliminate things, it changes the number of total elements you have. Like on theory, this is great, but there's a little bit more explanation that you need to do with this. So what this is saying is that, okay, I have two candidates. Right. So those two are the same. Those two are different. Okay. So if we, okay. If we do this, what we can say is that, well, anytime I eliminate a candidate or an element from one candidate, I eliminate it from the other as well. Okay. And what ends up happening is that, okay, well, we go with these two get eliminated, these two get eliminated. I have these two as the same, but I only need one representation of them. So this gives me this one. I only need one representation of them, so that gives me that one. And then when these two are paired up, I only have one representation, and bam, I have the majority element. Okay, so that is the basis of how this works. But it can get a little bit tricky, because what happens when you end up with something like need to make sure I get this right, because I mess this up all the time. Give me a second. So I need one more green. Does that work? Okay. 1, 2, 3, 4, 5, 6. I think this works, right? Yeah, 10, 6 screens. All right, cool. So I'm going to, this is going to consolidate, oops. This is going to consolidate to one green. This is going to consolidate to one green. This is going to consolidate to one red. This is going to consolidate to one blue. Oh my gosh, why am I having such a hard time? This is going to consolidate to one green. Okay, now we have here, and now we want to match them up again, right? So let's match up the green and the blue. Right, so this matches up and this cancels out, and then we match these up and this cancels out, and then we have a green left over. Okay, awesome. But what if we don't match them up like that? Because remember, the pairing is kind of arbitrary. What if instead we match up these two, which becomes one green? This red has nothing to match, right? If this red has nothing to match, what do we do with this red? So we have to come up with a idea of what to do with an odd number candidate. Okay, and this is why the algorithm has to expand out a little bit rather than just this is too simplified. This is not going to work, right? If you came up with this solution, while you can assume, you can make the leap and say, okay, well, I'm going to assume that my initial number of candidate is a power 2. That's fine. But when things are paired up and they eliminate unpredictably, you're going to end up with some cases where, okay, what if I have an odd? What if these greens were more evenly spread so that everything canceled out and you're left with one green? That works. But what happens when you have one red and one green, right? So we need to expand out a little bit. And so I think hopefully the solution we provided you does that. And then we can read it and we'll talk about it. I will say getting to this part is probably going to be a majority of the votes. I mean, so a majority of the points, because one, it is the optimal solution we are looking for, and two, you're getting most of the way there. You're just kind of not handling the case that really matters. But this will get you a lot of points. I don't know how these two answers would compare. My thoughts are that this is a little bit more advanced thinking than this solution, even if you're not quite there yet. All right, so what you end up doing is that you're going to pair up the elements A arbitrarily to get your n over 2 pairs. That's what the hint is. You're going to look at each pair. The two elements are different, discard both of them. They cancel each other out. If they're the same, just use one of them, because one vote represents those two. And because one vote represents those two at this level, and every level after it, it's either going to be one vote representing two or no votes at all. You maintain the majority as you go. Okay. Now, each time there is an odd number of candidates, okay, you take that element, you take one of the elements that you're left with, and you say, okay, I'm going to check the majority by comparing against all elements at the current level. If it is the majority, right? So if my red is the majority after I have I'm done. I have if I have one odd number left, if it's a red, I check against my entire row, or against this entire row. Is this red the majority? No. Okay. If it's not the majority, I'm done. I get rid of it and I continue. If I'm in the case where I end up with green, so I'm at a green in where if I have a green left, instead I go, okay, well, is my green the majority? And I check it. If the green is the majority at that level, it is the majority at every level, and so I can return that. That's done. Okay. What happens if, given what I did, I end up with one green and one red? Okay, I still have an even number at the end of this, right? These two greens cancels out. I have this green. These two cancels out, so there's nothing, and then this red stays. So now I have let's say I have a red and a green. Okay. When I'm down to two candidates like that, I'm just going to check both of them. Okay. So we have two elements left. Check each remaining element, 2 max, against all elements in the region A to see if either of them represent the majority. return this element if a majority exists. Because I could also potentially keep canceling down until I have 2, right? And neither of them are majority. If all my left side is, if I do something like this, I potentially don't have a majority at all, right? My red has combined to equal 1 share. My green has combined to equal 1 share, and green and red are neither of them a majority. So I always have to check to confirm, okay? And so the correctness is that if there is a majority x, then at least n over squared plus 1 of x exists, right? That's the definition of a majority in this problem. So after every round of elimination, x would remain the majorities because it would create more pairs than any other elements combined. Okay, if there's an elimination, an equal number of majority and non-majority elements are removed. Not equal, but like at worst you have a 1-to-1 removal. And then if there's a majority, it would still survive that round. We're just looking for whatever could survive that round as a majority. For each x not paired with an x, so this part's really hard, but you should understand. For each x not paired with an x, a non-x also does not get paired with itself, paired with x instead. So the eliminations are equal, and so it's okay. So x pairs always outnumber any other pair. If there is an odd number of elements, we can eliminate the extra element by checking to see if it is a majority element or not. We can tell right then and there. Finally, we check the remaining elements to max against the original array to confirm if it was a majority. The runtime here is the tricky part because you would think, okay, well, every time I have an odd number, I'm going to keep checking, and that's going to be all of n work. And so if I'm doing log n levels, isn't that just n log n again? But it's a little bit different because of the elimination of candidate at each level. I'm actually getting a smaller subproblem each time. Okay, so the recursive relation then is t of n equals t of n over 2. I'm doing half of, because of the eliminations, I'm checking half of that number of elements at each level. Okay, and I'm not doing more than one subproblem, more than one recurrence. I'm only doing one, and it takes all of n work at worst case, right? Because each level, I may potentially have one single odd element, and that odd element has to take all of n work to either confirm or eliminate. So it's all t of n over 2 plus all of n, which equals all of n. We split the problem in half each time. We do n comparisons at each recurrence. For a equals 1, b equals 2, d equals 1, this is all of n via the massive theorem. Okay, so that's one of our section of work. Now, when we get to the very end, we have to do 2 scans because we could have most have 2 possible candidates for majorities. So that's 2 times n. So we end up with 3 times all of n, which gives us all of n final runtime. So, and this is key here, because if you recognize the 2 solutions, you'll say, well, this is all of n work at each level. This is also all of n at each level. Where is the savings? I'm working with half the subproblem each time. I'm also working with half the subproblem each time. Where is the savings? Well, the savings comes from the idea that even though I'm working with half the subproblem, I'm not dealing with both halves. I'm only dealing with that half of the subproblem each time. And so the savings come from how many recurrences I have at each step, and that savings ends up with an O of n. It gets rid of the log n part. Questions about this solution? If you're wondering what's the difference between the hint and here, the part that's important is what do we do with an odd number of elements, and what do we do at the end to confirm that they are in fact a majority element. Jafar?
Okay, thank you. Another time. I have here three questions, not small, but the first one is a little bit not about for example, in the quiz. Here we have a huge hint. Basically, they are telling us what to do. We have something like this in the exam or not? Because if you ask me here, can we do it in off?
We will not be giving it. We will not be giving you a hint in the exam.
Yeah, but it will take me maybe hours to find the solution here. Maybe I don't know. It will be very hard to find a linear solution. Are we expected really to find this way of working?
I think so. I think you are now. And so I dug really deep into this on the first office hour, and I think it bears repeating. If you are struggling with these homework or the practice problems, you are expected to. If you are able to come up with a solution to this problem in 10, 15 minutes, 20 minutes, maybe even 45 minutes, there is no value in you taking this class. You have already mastered the craft of answering these questions within the exam time. The whole idea of you being in this class is to learn how to get there. Now, if I gave you this problem as is on the exam without ever having covered anything like it, it would be extremely unfair to you. You would not be able to solve this within 45 minutes or actually less, however many times, right? You would not be able to solve this, and it would be not fair. Now, having seen this problem, having gone through trying to solve the problem, having seen the solution, having seen the solution explained to you, if I gave you a similar problem with a few tweaks here and there, a few boundary conditions a little bit different, maybe a slightly different type of data that you're comparing, or a tournament solution, but not quite this, it now becomes fair for you to solve this problem on the exam in the limited time that you have. So that is what you're trying to get to. Do not consider struggling on this problem to be your end state. That is not what you are here for.
Okay, thank you very much. Now, two questions. One about the logic of the algorithm and one about the runtime. Okay, about the logic of the algorithm. Can you scroll up a little bit, to see the screen? Yeah, here. So if we start by 2 green, 2 blue, or let's say I don't care about this one. So 1 green, 1 blue, 1 green, 1 red, 1 green, 1 blue, 1 green, 1 red. Okay, so we'll only have the majority from the first one. But it's still, we have greens enough to have the majority for the full problem.
So, all right, let me see if I can get this going. So what is so you're saying 1 green?
First of all, 2 greens, and then 1 green, 1 red, 1 green, 1 blue, 1 green, 1 red, 1 green, 1 blue.
You said 1 green.
Yeah, it's fine. It's fine. Yeah, anything.
Okay.
Even this is enough. Yeah, maybe this is enough. I think yes.
Yeah, this will work.
So okay, but my question is about the logic of the algorithm. Maybe I did not understood it. So here we only have one majority, which will bubble up from the first one, which is the green.
This will get eliminated. This will get eliminated. This will get eliminated. This comes out to be 1 green. So now we have 1. So this is why it's up to 2 candidates, but you have a most of candidates. You could also just have 1. Now at this point, when we're left with 1 candidate, we're just going to compare it against all of it.
Understood. So I compared about against everything inside the full list. So it's O of n.
Yep.
And then I found out, yeah, it's a majority. Wonderful. Now, if we add one red, 1 red, and 1 green, 1 green.
Sorry, hold on. We add one red, 1 red.
And 1 green, 1 green.
1 green, 1 green.
Okay.
1 green. Okay.
So the red will bubble up also.
This becomes red, and this becomes green,
will
right?
bubble up. Yes.
Yes. Okay.
So if you compare, so we either compare the green with the red, so both will be discarded, and then we will only be left with the green.
Yes. Okay. In this case, right, you have one odd, right? You have an odd number. So we take one of them and we check to see if it's a majority. So let's say we do red. If we do red and we checked against it, and red is not the majority, we end up with 2 greens, and this gives us the final one to check, right? So that's one thing which happens. The other thing that can happen is we arbitrarily chose 1 green instead, right? So we are going to check this one, and let me just make sure. 1, 2, 3, 4, 5, 6, 7 out of So there's 7 of these across 12. And so this is a majority, and so we immediately return. So whenever there's an odd number, you have either a potential of eliminating one of the odds, or you have the potential of finding the majority immediately. And because this is all of n work, on each subproblem getting smaller, it'll work.
Okay, I understood the algorithm. Now going to the final thing, justifying that there's only 1 t over 2, not 2 t over 2. I did not understood what's the difference. I know that there is elimination, we are eliminating things, but how to understand that the recurrence is T of n equal to T of n over 2, not 2 times T of n over 2.
Right.
This is very...
So you understand, yeah, so you understand the n over 2, right? I have divided my subproblem into
Yes.
a,
Yes,
you know,
yes.
one set. Okay, so at most, I'm going to have n over 2 subproblems.
Yes.
I'm just going to run my algorithm again directly on top of that new subproblem. So that is one recurrence work on half of my initial, my previous number of subproblems.
Okay.
So the A here equals 1, B equals 2, and I'm doing
Understood,
O work.
understood. Okay, okay. So because we are only calling one recurrence in the full algorithm, so if we write it, we will only, okay, we divide things into two, and that is basically
and then you
all.
run.
And then I run it, which is T of n over 2. Okay, understood. Thank you.
Yeah. Whereas in part A, we are dividing into two subproblems, and then we further do work on each
on
subproblem.
200%.
Yeah.
Yes.
So it's all that gives us the 2 times the T of n over 2.
Thank you very much.
Yep. All right. Lots of questions, so let's try to get through. Bing.
Yeah. Well, I just want to clarify, because in the runtime analysis part, just the verbiage of preciseness, is it enough to say, just like the simple solution says, we split the problem in half each time, where in reality, you know, because things can cancel out, like both get discarded, right? Quite often it will be less than half after each iteration. It's okay to just say half, because it's the worst case scenario, right? Okay, yes. So we don't have to keep adding at most, at least, these kind of things, because we're already under an assumption it's the worst case scenario analysis. Same as the ON component, like we have to deal with odd elements, just assuming we have to deal with odd elements each round.
Yeah.
We don't have to repeat like in the worst case again, right? Okay.
Yeah.
Okay, perfect.
You take whatever you're doing and you assume every time that you can do work, like every time there's a decision whether to do work or not, you assume you have to do the work, and that should be what drives your ultimate runtime.
Fantastic. Thank you.
Reese, I think I skipped you. I'm sorry about that. What's your question?
No problem. So in part A, we describe breaking up the list down to its individual elements. So on part B, we are just saying you get n over 2 pairs. Why don't we have to describe like the process that we go through to get that list split up into those pairs?
Yeah. So let's see. Okay. So it's a little bit you can actually do it that way if you wanted to say, oh, I'm just going to split everything up into pairs and then I am going to bubble up. That's actually also fine. I think what this is doing is that it's actually tracking how merge sort kind of works, and that you go into a subarray, you further divide it, you further divide it, further divide it. I think either way is fine. I think you can write it either way. Doesn't really change the logic with the solution much. Go ahead and do whichever one's more comfortable.
I'm just worried like going through and splitting those pairs, that could give us the like O of n or O of n over 2 runtime there, and that might mess with our final runtime analysis. Is that something to be concerned about, or we just assume it's like leaving off from where the merge sort ended on part A?
I don't think it shouldn't change your runtime. It's just the wording of like how you are dividing, right? Like we simply divide the input into 2 equal size subarrays. You're basically going to get to the point where if you started off with like divide everything into a single subarray of 1, and then move on your way up to combine the results and figure it out, that's fine too. If you wanted to from here say divide, start with keep dividing subarrays into 2 until you get to a subarray of a pair, and then go do your thing on the way up, that's also fine too. I think it's just a wording choice here, not really a difference in the runtime or how it works.
Okay, thanks.
Yep. Prakash?
Hi. So I see the second. So it says when you have this extra element, you compare against all elements at the current level. But what is the current level? Is it the one where we have the extra element or the one previous to that?
So you're doing work at this level, right? And you are ending up with this. And so if you have an odd number here, your current level is right here.
I don't think I'm seeing the cursor on your screen now.
Why? Do you see it now? No?
Yeah. Yeah, it came up for a
Oh, you
second.
see it?
Yep.
Okay. So at this current level, right here, we are making our eliminations, and then we end up with an odd number, and then we take one, and we check against this current number, this current level.
It went away. I don't know which one you're referring to as the current level. The top one or the
Okay.
bottom one?
Okay. I got you. Right. At this current level, we have done our eliminations to get our potential candidates. If we have an odd number of candidates, we check that odd number candidate against the current level. This is the current level. Because your next recurrence is going to use those candidates. So your current recurrence is based on how you got those candidates.
Okay.
And that can probably be cleaned up a little to make it more clear, but that's what it means.
Okay. And if we go back there, if we actually check against the second level where we have this elements, odd number of elements,
yeah,
why would that not work? And you will be checking only half the elements.
Because I showed it, right? Because if I happen to have this green, blue, red, and green, right? Like if I could potentially lose. Like, what do I do with this odd element? I don't have anything to pair it to. My steps doesn't say anything, and I can't just keep it. If I just keep it, I could potentially make, because every level you go, it's representing more and more number of candidates, right? Like this one is representing 2, this one is representing 2, this one is representing 2. So if I take this, where I only have 2, and I move it to the next level, I am now representing 4, or potential, up to 4. But when I only really have 2, so I can't just carry it forward. I also can't just eliminate it, because if I just eliminate it, I've lost all track of how many I have here. So you have to process it right then and there to see if it's a majority or not.
Okay.
Whether it's a majority or not is unknown. Keeping it forces me to make it represent more elements than it should. Removing it forces me to not consider elements that I should. So I have to process it right now.
Okay.
Nishink?
Hey, Jovis. So are we allowed to be like a little bit ambiguous in like the algorithm part, like when you say like pair up the elements of A arbitrarily, or take one element and check if it's the majority, because that's like that it doesn't affect the final solution, like regardless of how you do those?
I don't think either of those statements are ambiguous. Arbitrarily is very much distinct in that we don't care. We purposely have said we don't care. Arbitrary does not mean that it's unknown how we do this. We purposely say it doesn't matter how we do the pairing. The words of check if it is the majority is followed by how to do that by comparing against all elements at the current level. So that is also not ambiguous on how to check for the majority.
Okay, thank you.
Yep. Bradley?
Hey, yeah. My question is on the last row, or the base case where you get to 2 elements.
Yep.
I'm struggling to
at most two. At
most 2. Yeah, it could be 1 or 2. I'm struggling to wrap my mind around why you actually need to do those comparisons to the original A. I can't come up with an example where that's the case. My reasoning is that wouldn't you be able to get down to 1 element every time? And if they don't pair, then they aren't the majority, because they are at most 50%, aren't they?
Let me see if I can come up with a good example. I should come up with like a already made graph of these.
Yeah, I tried coming up with a few and it wasn't working out for me. But I'm sure that there is an example and reason we need it. I just couldn't think of one.
Yeah, gotcha. Okay. Notice how green here is not the majority, right? And notice how red and blue. Okay. So if I happen to pair up the green and the blue and the green and the red, everything gets eliminated. And that kind of works out. But if I happen to pair the greens together, I have that situation, right? And if I happen to pair the blues together, these get eliminated, right? So now
no, yeah, I understand in the single node scenario that you would need to check it. My thought was more in the two node scenario why you would need to check both of them. Why can't you just go down to one node every time?
Oh, okay. Let me see. I'd have to come up. I'd have to think about it, but I do know that we did this because it actually can happen.
Okay.
Maybe we'll try to find an example. Yeah.
Sure. Let me play around with it to see if I can think of one.
Yeah. Okay. Matthew.
Yes, hello. Two quick questions. Can you confirm, firstly, why this is not log n like binary search, where the worst case is splitting in half each time on each level? Is it because
so you can use the master theorem to do the numbers and it'll work out that work this out. But what ultimately happens is that this O of n work is going to dominate your number of subproblems and your number of recurrences according to those subproblems. And so the O of n ends up being the most amount of work. Like if every time if I divide my, like think about it in like a very simple manners, right? If every level I have is O of n and the number of levels I have is 3, right? Obviously the O of n work at each level is multiplied by 3 and it dominates however many levels I split into, or however much subproblem recurrences I set up to. Now, if my work of O of n ends up being O of 1, like it's O of 1 work, but I end up splitting into a lot of subproblems and a lot of recurrences, then that part's going to dominate. Now, there happens to be a sort of a break-even point based on, if you go look at the math theorem, that when they equal, you combine both terms. And when one is absolutely more than the other one, it ends up mattering a lot more in the overall runtime. And so that happens in this case. Yes, it's log n split, but because you're doing O of n work at each level, it ends up dominating however many subproblems you end up coming up with.
Got it. Thanks. And secondly, real quick, I just want to understand why we did not have to explain how in your algorithm you have check if it is the majority by comparing against all elements at the current level. I guess that was enough detail. Like, why did we not have to go further into details on how we check majority there?
Because we already explained it. I mean, I think we would just look for one part, like, if the two check if it is the majority by comparing against all elements at the current level. Like this statement is still the same. Like you don't have to repeat it over and over again. Like, it's one of the things that you have to explain once, and then you can use that same explanation assumed later on, right? This is how I check for the majority element here. Next, I also check for the majority element. I wouldn't have to say how I do it again.
Got it.
Okay, Shinak.
Hey, hi. Thank you. I have a quick question. So for the same statement that you were referring to, if we have one odd element, we arbitrarily pick one up and check at the current level if it is the majority. Why don't we check it on the original list rather than the current level like we do at the end?
So if you do that against original list, your subproblem does not get smaller. It becomes T of n plus n. It's all of n work based on the original list of all of n, and that's actually a lot. So you end up with, I don't know, you end up with a much higher runtime. The reason why you can do it less is because at each subproblem, if you can confirm that the majority is the majority of that subproblem, it is also the majority of the all of your entire level.
But then how is that different from the last check? Like if we end up with 1 or 2, like the max of 2, we still pick whatever we have and check on the original list. Here I'm understanding if we get one odd element and if we see that at the current level it is the majority, we exit and say that that is the majority. Like why is this difference?
It might work. I think it could work. I have to think about it, but that might potentially also work. If just not to check against the entire thing, just check against the previous level. I have to think about it.
Okay, I mean, in the example that you showed, if you had 2 green and 2 red, and if we match up the 2 greens and the 2 reds, we end up with 1 green and 1 red. In that case, even if we check it at the previous level, I don't know if it is sufficient to tell it is the majority.
Right. So in this case, there is no majority, right? Yeah. But if we had a green, I think it can work. I mean, a lot of these solutions are just written in like, this is how we came up with the solution. It doesn't mean this is the only way that it'll work. Like when we go grade it, if your solution works, it works, and we'll give you the points for it. Like no matter what I write here, or no matter what the solution is presented here, someone's gonna say, why can't we write it this way? And the answer is you can write it that way. It could still work.
So sorry, like I was just trying to understand why it would be correct. Like if we check it at the current level, if we have an odd element and it is appearing as the majority or not appearing at the majority, like are we confident that it is the correct answer? That's all I'm trying to understand, because it seems like we are treating the two cases differently. What hence ends up at the end is being treated differently than in the intermediate stages if we do have like an odd number of elements.
Why is this being so annoying? I will have to consider. I will have to look into why we end up doing it that way. I I think it'll work if you just check against the current level. I think the majority has to carry forward, and so you probably just check against the current level and it would work. You don't check against the entire array every single recurrence because that potentially blows up your runtime. I think the final thing was just like it doesn't really matter if you check against the current level or the entire level, your runtime remains the same because you're doing 2 work at most. But I do think that if you check against the current level, it should work.
Okay. Yep. Thank you.
Yep. I'm going to answer a couple more questions and I'm going to try to do the last problem. Saeed?
Hey, so I don't know if you answered this, but can we use fast select algorithm to solve this problem? Setting K. Oh,
wait. So I went over specifically why fast select doesn't work on this problem.
Okay. Can I
So
still
if you
just propose what I had in my mind? Because in my mind works, or at least the paper works. Just don't know if I'm not seeing something. So if I'm setting my K at n2 plus 1, if the K is even, if the n is the even, and n2 if it's odd, and finding that element basically next to the median, right, on the left.
So you don't have a median. You don't have a median in this problem because there is no comparison. The values cannot be compared to be a less than.
Oh yes,
right.
Yeah, I missed that. Right. Makes sense. Sorry.
Yep. No problem. Bikash?
Hi. So that was a very interesting question. The one before that, where we were looking at why compare the previous level or the current level at all of the places except the last one, where we compare with the full array. And I think both of those are right. So I think at any level, the children will have a majority only if the parent level has a majority. And I think if we try with some examples, we'll see that there is no way that the children will have a majority if the parent do not. So I think even at the last level, if you just check the current level, it should work. But I do want to come back to that other point where if we just check with the full array every time instead of current level, I'm not saying why that would be not O of n in total, because even in merge sort, that's what you do. At each level, you basically combine the whole, you go through all the elements, right? Even if it is like, multiple subproblems. And that's why you have O of n there, like T of n by 2 plus O of n, because you go through all the elements and not O of n by 2. So if we check with the full array at each level for the odd elements, I think it will still give us the same runtime. Am I understanding that correctly?
Wouldn't that be n log n? Because if you're doing O(n) at each round, you have to do log n times at worst. So that would be n log n.
And that's because it won't be log n, because we are not checking both the subproblems. We are only checking one of the subproblems, so only one of the lag. That's how I understand that you will not have that log n issue.
Right. So this solution is O of n because you keep dividing up your subproblems smaller and smaller, but you only end up working with half of your overall subproblem at a time. So it doesn't get that log n work. You just get that O n which dominates. The reason why merge sort is O of n log n is because whenever you did that O of n work at you do log n times do the O of n work, but you're doing it twice because you have it on both subproblems, and you have to do it. You have to fully process all the subproblems. You don't eliminate any of it. So that ends up being the long time runtime with the O of n log n.
Right.
I would say, hold on. I would say instead of trying to understand what the runtime is based on the logic of it, work out your master theorem equation. Write out the equation, note that the two equations are different, solve for that equation, and you will see that the runtimes are different. Now, what you need to be able to, get compressed together is, why does that equation equal that runtime for one problem, and why does that equation equal the other runtime for the other problem? You have to understand the relationships of those. But I mean, it's clear that the equations are different, right? That should be clear. Hopefully, that one of them is I'm doing work on both subproblems. One of them is I'm only doing work on one of the subproblems.
Yeah, I think that makes sense because one has T of n equal to T of n by 2, and the other one has like 2 T of n by 2. So I think that's causing that log n, because the merge sort has 2 Tn by 2, not just 1 Tn by 2. But the point that I was making was, like, at each level here, we are checking for that odd element out, and if we check against the full row, full array, it will still give us the same runtime.
It does not, because your full array is no longer. So the reason why that plus O of n works is that because your T of n over 2 is making your subproblem smaller and smaller. The second you have to do that O of n work across the entirety of the original array, you're no longer doing it at T of n over 2. You're doing it at you're doing it across the entire n, which is T of n, right? You're no longer getting smaller subproblems because each step is working on the full array. You end up with because you're not getting smaller subproblems. Does that make sense?
So what I actually meant was, you are still doing the subproblems at every level. You are still having Tn by 2, but when you have the odd element out, instead of finding the majority element in current level, you use that odd element and to check if it is majority element in the main array, main entry, main list of array, right?
So this O of n right here, this O of n is in relationship to the size of that subproblem. So if your subproblem is always going to be the full array for that O of n work, your subproblem never gets smaller. Even though you have a smaller subproblem, you end up doing all the work every time. So you're not getting a smaller subproblem in the actual measurement of the runtime.
Okay, got it.
Yeah.
Okay.
How much work is it across the subproblem that you're working with? If it's across the entire subproblem, then your subproblem getting smaller affects how much work you're doing. If your subproblem getting smaller does not affect the work you're doing, then you end up with a T of n. You're not actually getting subproblems. You're just doing part of your algorithm on half of it, but the majority of it is still across the entire initial problem, and your runtime is going to be based on that.
Got it.
I am really going to answer one more question because I think I have one more problem to cover. Bing, your last question.
Yeah. I just want to clarify the recurrence relationship in the scenario he just proposed. So right now it's written as T of n equals T n divided by half plus On, right? Because the On part is for if there is an odd element, we'll do one time of comparison of all elements at the current level, right? Because the T of n passing n elements, that's why we're doing O of n. But like when he said it's for the whole original array, how do we even present that for the second part? Like, how do we even show that mathematically?
This is it. Because you're not actually dividing it by any subproblem. You're just doing it across the entire n, right? So like, if I told you that, hold on. If I told you that I have a big array, and every time I have to do something across that big array for one step, and the second step is across half the array, what is the dominating factor of what my subproblem division is? My subproblem division, even though some of my steps might only work with half the array, if my overall big step that I'm doing is across the entire array every single time, I am never actually getting smaller subproblems. I am always working across the entire array. That is what's dominating the work at each recurrence. And so it's actually T of n. Your T of n over 2 means once I have split the subproblem in two, I only ever have to work with half of that subproblem. The second I have to expand that across the entire input, I am not dividing anything into subproblems anymore.
Does that mean there is actually no OM part anymore? I'm just trying to understand what do they each present. Because when you say that there is no subdivision anymore, so T of n is literally equal to T of n, because the odd element comparison is already part of this, right? So do we still have a separate plus O of n part?
Yeah. Yeah. You're okay. Your A is equal to number of recurrences.
Right.
Okay, so we agree on that, right?
Right. Well, maybe we should start from the original one, the correct one.
No. Okay, so B is equal to size of my subproblem.
Right.
Right.
Well, the division of the
Or division. Okay. Your D is equal to some exponent of, where the O of n, this part right here, is work on subproblem. Okay.
Right.
Okay. Okay. You cannot try to force your algorithm to be faster by saying, let me take a n size array, right? Divide it in half.
And then still goes through the whole thing. I get that part.
Hold on. You cannot say, I'm going to divide my subproblem into two things. I am going to do step one on this half, and step two on this whole thing. And because at some point I only worked with half the subarray, that my subproblem division is n over 2. It doesn't work like that. If your step two uses the entire subproblem, you have no division of subproblem.
There was no division. I totally get that. That's not my question. So the question was, the original recurrence relationship is T of n equal to T n divided by 2 plus O n.
Right.
My understanding of that is the T of n divided by 2 represents after each round of elimination, whatever. At worst case, you'll still have half of the elements. You still need to go through this algorithm again. That's why it's a recurrence, right? Plus the O of n, which represents
which is the work on that level.
Yeah, you have to check the odd elements on that level. But when it's running the algorithm at checking against the original array, you said it's no longer subdividing, which I totally agree. But so the first thing wouldn't be Tn divided by 2 anymore. It would just be T of n. But wouldn't that also remove the O of n on the right, because you are no longer doing that item, the level checking for the odd element? I'm just trying to understand, like, do we still keep the ON part there, or like what does that represent in that case, since we are no longer doing the odd element checking at the item level, but at the original array? So does that mean we remove the right side and it's literally not doing anything? It's just T of n equals T of n.
No, you still have to have the O of n, because that is the so if I keep passing down this T of n, like if my subproblem doesn't get divided, right, and I keep passing it down, how much work I'm doing on that subproblem still matters. I could be doing all of one work, right? I could potentially have T of n plus all of one, which means that my subproblem is not getting any smaller, but I'm doing very little work. But if I'm doing my subproblem is not getting smaller, and every level I am going to check across the entire array of what I'm working with, that's still all of n. So it's still going to be T of n plus all of n. There's a distinction between T of n plus all of 1 and the T of n plus all of n.
But wouldn't be all of n actually be bigger than n because you're checking against the original array rather than just at that level?
I mean,
It
at
could
that
be
level,
exponentially bigger in the bottom level, right?
no, because your work across that level is going to be the same size as your subproblem. Yeah, so it's the all of n represents how much you're working with that, the input of your subproblem, right? And the input of your subproblem is 2, your all of n is 2. If your input of your subproblem is 5, your input to your work on that is 5. So that all of n represents how much work you're doing on the subproblem. The problem with doing it across the entire array each time is that subproblem never gets smaller. And that subproblem never gets smaller, your work doesn't get any better at each subproblem.
Oh, I see. I see where the confusion came from. I thought all of n part only represents the cost for checking that odd item at that level, but that actually includes the cost also for comparing each pair of thing and decide to discard or not discard, like keep one. That's also part of the OFN.
It's just whatever the dominating piece of work is at that level. Yeah, I
Okay.
mean the dominating work at that level is the odd check every time. If you do not make it smaller or check a smaller subset, you end up doing all of n work every time without any subproblems smaller.
Yeah, but we still have to check each pair and decide to discard or keep one, right?
So
and that still
at this
has
point,
to go through Ellen.
hold on. I really have to move on to the next problem. I think I've discussed this problem basically to the point that I can feel comfortable with. So I think I need to move on to the next one. Sorry,
no
everybody.
Thank you.
Yep. Okay. I'm going to paste the entire problem and just talk through it. I think this one is actually relatively simple. So we don't need to separate the two. Okay. All right. So the binary search modified asked the question: design all of log n time, except again, we probably will not give you the runtime on the exam, so be careful of that. But that does tell you that you're doing binary search, right? Plus the problem is called binary search modified. To find the smallest missing natural number in a given sorted array of length n, right? So that's another key clue that you're trying to find something in a sorted array that almost always leads to binary search. The given array only has distinct natural numbers. Typically, when you are given an input that has special modifiers of like, oh, these numbers are natural, they are distinct, it has some meaning, and there's going to be some reference to it in the correctness. So be careful of that. Why does distinct natural numbers matter? Why can it? What happens if it's not distinct, right? Does your algorithm work if it's not distinct? So keep that in mind. And if we do give you something that says the numbers are distinct, use it to your advantage. It probably means that the algorithm that you have to write that works with non-distinct numbers is going to be a little bit more complicated. So be sure to take advantage of any limitations that we put on the input for you. So for example, the smallest missing natural number for A345 is 1, because 1 is supposed to be in the array, but it's not, so it's missing. Okay. A equals 1346, the missing number is 2. Okay. So again, like I said, you want to do a modified binary search, and you're not looking for a specific number because you don't know what that specific number is. You're looking for a number that's missing, and how you know that number is missing can be compared with the number that's at the array, in the index of the array. Okay. And again, multiple numbers can be missing, but you have to find the smallest one. Okay. To solve our problem, we will modify binary search in the following way. Once the midpoint index is found, and don't have to tell us how you calculate midpoint, we assume that is taken care of for you. We check if the value at the midpoint is equal to the midpoint. Okay, that is if A of mid equals mid. Okay, if it's not, and this is where your branching strategy has to be very clear to us. If it is not match, that tells us all the expected values to the left of the midpoint are in place. Okay, so it recurs on the right half of the array. If the value is greater than the midpoint, we know that there is at least one missing number to the left. Okay, because there's a gap, therefore it shifted the array enough that your midpoint is greater than the number that you expect, and so you recurse to the left half. Our base case is that when we get to a single value, so everything's been eliminated, we check if the value of I is equal to its index I. The first missing number is the value immediately following that. If the value does not equal the index, then the missing value is the index itself. Okay, we return the missing value. Okay. Okay. Let's see. Okay. Justification of the correctness. Why does it sort? Well, our input is natural numbers sorted in non-decreasing order, which allows us to take advantage of binary search. Okay, we explain why we are going to use binary search. As natural numbers begin at 1, then because the elements are distinct, the missing number must be the lowest I, such that A of I is not equal to I. We check when we check if mid equals mid, if they match, we know all the values values 1 to mid are present, and must search the right. If they don't, then we search the left. Okay, continue searching left. Why is the fact that distinct numbers are important? Because the numbers are distinct, if the lowest value of I if A of I is not equal to I, that tells us something. That tells us which way to shift. And if A of I equals I, that tells us something on which way to shift. If numbers are not are allowed to be the same, a gap could be filled with the same with a different number, and you wouldn't know that there was a gap, right? So if we have this 1, 3, 4, 6, right? The only reason why we know 2 is missing is because when we go to check either 3 or 4, depending what the midpoint is, it's shifted, right? But if I was to fill in this missing 2 with a 1, say 1, 1, 3, 4, right? 3 now is in the right place, even though we have a missing number. 4 is also in the right place if we have a missing number. But because they're distinct, it allows us to make take the idea of that if there's a missing number, it's the lowest I that A of I is not equal to I. Okay, so having that distinctness matters. Runtime analysis, it's binary search. We've made a modification. The modification is all 1. That doesn't change the runtime. So a modification to binary search simply changes the comparison and return value, and both changes remain constant time, and therefore it's all been locked runtime based on binary search. Okay. Any questions about this problem and solution? No questions? Awesome. So if we have no questions, oh, sorry, Stephen.
Hi, yeah, sorry. I just had a quick question about basically a general question about the class, and so more specifically kind of the format of the test, because like, we're going over every question we're having here is like this exact format, like, algorithms, justification, correctness, and runtime analysis. Is this like every single question on the test basically asking in this format essentially, or?
Every divide and conquer problem will be asked in this format. Yes, not the dynamic programming,
oh, yeah.
and,
of course,
and possibly not the future problems, but every written problem will be asked in this format. Now, there may be some multiple choice questions where it's asking for a very specific part of this rather than like, write out this format. But if you're given a written problem and it's divide and conquer, we're looking for an algorithm, a justification of correctness, and a runtime analysis.
All right, sweet. Thank you very much.
Yep. Reese?
So follow up to Steven's question there. Will we have a section, or will sections of the tests specify whether it's like divide and conquer or anything like that, or is that something we have to determine based on the wording?
The written problem, so you will get multiple written problems. One, some that'll cover. I don't know what the breakdown of the exam is, so I'm not going to get into it. But the problem that's divide and conquer will say give a divide and conquer solution. The problem that is dynamic programming will say give a dynamic programming solution.
Okay, thanks.
Yep, Anna.
Hi, I think I have two questions. First, for the exam, will it say like you have to give the algorithm justification of correctness and runtime analysis, or should we like remember, okay, for all divide and conquer, those are the three things that we need to provide?
I do not know. So the exam hasn't been written yet, so I don't know. Like sometimes we change the wording, sometimes we change it. So I do not know, but it's always good to remember it because, you know, it's three things should be you should be remembered. And then so before we continue, I will say that I do have exam prep office hours like next week and the week after. I'll go over a lot of more practice problems and you can ask more questions about it. But in general, if you ask me questions about the exam right now today, it's not written yet, so I don't have all the answers to it. So you're probably gonna have to ask them again later. So I would hold off on any exam tough questions until future office hours.
Thank you. Other question was for dynamic programming, I think like you guys very much said everything, the input should start at 1, not at 0. Is that the same like assumption here? Because for this problem, it seems like also we're indexing starting from 1.
I would say always index from 1 in this class. And if we don't give you a indexing, it's typically, you know, I mean, the answer here doesn't use it. It doesn't really need it. But I would say, yeah, as a good practice, always index from 1 in this class. Unless it's code, then your code can do whatever. Michelle?
Hey, Joves. I had a quick question. So for our base case, when we get to a single value, just before that, if you have two values, I guess how would we, which value would you consider the midpoint, the first or the second?
You can assume that your binary search will do the right thing. If not, if that's uncomfortable for you, just when you have two values, check if the first value does not match the index, or if the second value doesn't match the index. Whichever is the one that doesn't match is going to be the one that's wrong.
Okay, got it.
Yep. Any other questions? All right, great. Good, solid office hours. I think everybody got to learn something. So starting next week, I believe we will not have any other topics covered. So I will be going over some of the suggested practice problems. These are ones that don't have solutions, and I will try to cover them the best I can. Come prepared to have done those problems, because otherwise you're going to be completely lost when I go and explain them. And I will mostly not be covering too much more on the subject itself. You will have watched the lectures, read the textbooks, done the practice problems. So I think that will be like lost time if I did that. I will go over quickly some of the things I covered, just so students who didn't get to see the previous office hours will know that they were covered before and to go look back at them. But I will mostly be focusing on solving problems in the next office hours and beyond. That's it. I see, Robbie, you have a hand up. So this is my last question, and then we'll call it a night. Robbie?
Yep. Thanks, Joves. Quick question. After we get our homework results back, is it possible to go up to like retry the homework and with the understanding of what you did wrong in your homework? Because I have a feeling that in the first homework I messed up somewhat in the homework in the first homework. And I want to know like where I went wrong so I can go through that again. Is that possible for that in the second homework?
Yeah, so in this class, we try to embrace sharing of collaboration between students. So if that's what you want to do, what you really should do is get back your feedback, and then if you don't think you did well on the homework, retry it, write a different solution, and then post it in the into the homework thread or the feedback thread, and just say, hey, I decided to write my homework one over again. Can someone who got a really nice score, or take a look at this and see if it matches what you wrote a little bit more closely. We want students to help each other out by providing feedback, and I always say that the best way to learn a difficult topic or any sort of topics is to teach others. Teaching the topic to others gives you far more understanding than you possibly could have learning on your own or learning from others. When you have to change your perspective on how a solution happens or how you approach something so other people can understand what you're doing, you add additional views or additional perspectives to how to solve a problem that you never could have came up with on your own. So I absolutely suggest students leverage that situation and just have other students critique your work.
Yeah. Okay. So like, because I was thinking I would do homeworks 1 and 2 again, greater problems again, and make sure without looking at the solution, and then I get help from other students.
Yep. That's
thanks,
a
Joves.
good idea. Yep. All right, everybody. I will see you next time.
Thank you very much.
Thank you, Joves.
Thank you.